Welcome back, everyone. We are here for day 4 of the completely free CCSK Certificate of Cloud Security Knowledge training course brought to you by GoCog Careers. And again, this is to prepare you for the CCSK V5 exam and the CCSK V5 certification. I'll be your host throughout this session. If you've just joined us or you're just seeing this video for the first time, I want to let you know that we have 3 previous days that you can go back and find. My team will drop the links to the 3 previous days in the chat box. You can find them and you can find them easily. I also want to let you know that there is a companion guide to go along with this. My team took our training materials and they created an e-guide, study guide for you. It's about 400 pages or so, a little more than that. So it's fairly comprehensive to help you in your cloud security career, your cybersecurity career, or even NPAS, as well as passing the CCSK exam. So sign up for it. It is completely free. In the description of this videos, you will find our guides on how to become a cloud architect or how to become a security architect or how to become an AI architect or enterprise architect for that matter. There'll also be guides on how to win the interview, how to prepare for an interview, and so many other things to help you in your tech career. And they're all free. So make sure you sign up for one while you are here. If you've been enjoying this content thus far, well, actually, we haven't really done any content yet today, so I don't want to say that yet, asking for likes, because if you've been here the whole time and you're having a great time, yeah, give a like. But if you haven't joined us yet, wait for us to show you how good the content is before you give a like. I wouldn't ask you otherwise. But so kind of keep that in the back of your mind. If you do enjoy the content while you're watching, please subscribe to the channel because we've got this and so many other things, other security programs on our career that are on our YouTube that are free with us, like the CISM training or the CCSP training for cloud security, for example, or CCNA training for networking, or AWS Solutions Architect training and Azure Solutions Architect training, at least certification training. That's all on our website free. So take advantage of some of these resources while you're here. So I want to know where you're from. Let me know where you're from. I see Patrice is in Miami, which is great. I'm also in South Florida today. Balraj, it's good to see you. So tell me where you're at. Let me know in the chat box where you're at. And give me a hashtag CCSK. And when I see that, we will start the training. I know you guys are awake, alert, and oriented. Well, I can tell you in Port St. Lucie right now, it's about 80 degrees outside, nice and sunny. Love it. We have people in Ghana. Love that. Miami. I'm sure we have many more other parts of the world too. But you're South Carolina. I love that. Philadelphia, Brian, that's an area I know well. My wife's there right now. More people in Miami. Eddie, I know Eddie. Eddie's in Cameroon, so I know where he's at. All right, Chris, let's go roll with the content. We'll get everybody started for the day. Now, how do we secure a container or a container images? Well, we have to manage security challenges throughout the entire container lifecycle, from the time we create the image to the time we deploy them, the time we delete them. So where do we deploy them? Well, we can either deploy them on a virtual machine, like we do in the data center, or the public cloud, where we basically get a virtual machine. Maybe we put something like Docker on it. We host our virtual machines on there, and we have complete control over where it's at. We can also use the fully managed container environment, where basically we just upload our containers and the cloud provider does it all for us, and we have absolutely zero control and we know nothing about it. For example, AWS has Fargate, where you can host your containers. Very simple, very elegant. You just put your container there and it's running on their service, and you don't have to think about container runtimes, virtual machines, or anything, but you lost the control. No matter what it is, there's going to be something going between you and the provider. You're going to have more to manage if it's in your virtual machine, but you're going to have more to control. And you'll also have the less to manage and less to control if you use a serverless option. So let's talk about building and creating containers. Remember that container image is going to be a lightweight executable package that's going to contain the code and the whatever app dependencies and settings are needed. And basically, they're typically built, there's build instructions in like a Docker file, for example, that'll ensure consistency and portability. Now, these things tend to be immutable infrastructure. So once a container is created and deployed, they can't be modified. They can be replaced with new images, but not modified. So you're going to want to use secure images. And you're going to store your images in secure artifact repositories to protect them from harm. With containers, we have to understand that it's more of an extension of the host networking. It typically leverages the host operating system, often Linux, for its network functions. Kubernetes, I think, has a similar concept on multiple levels, individual containers to application-aware load balancers, for example, ingress controllers. And we might be dealing with network policies and various technologies that can define the network rules and isolation. These could be provider-managed, self-managed, depending upon the kind of deployment and approach we use. Now, when it comes to containers, we have two things. We have runtime, and we have the runtime modules themselves, and we actually have the container orchestration. So something has to orchestrate the containers, where they are, what they do, that kind of thing. So what it typically looks like is you'll need to have a control plane. And mind you, you're going to see the same kind of thing for everything. So we might have a K8 control plane where we have 3 servers, and each one of these 3 servers manages where the containers are going to be. And then, of course, we have that. If this is the control plane, we have the data plane, and these are going to be the containers that are going to be running somewhere. But there's a control plane and a data plane. And the reason we need this is we can specify in the control plane that we need 5 container images. And for example, if we specify 5 and a container crashes and we had 5 and now we have only 4, another container will be spun up. So, and it comes with a couple of options. We can build and manage our own Kubernetes environment. It's open source. We can also use the cloud provider's Kubernetes environment. But in the world of multi-cloud, let's talk about the risk of that. So, for example, if we used an AWS Kubernetes environment, and the AWS Amazon EKS is great, Microsoft's AKS is great, and Google's EKS is great. They're all great. But I'd like you to think about something. Let's say you are in a multi-cloud architecture where you've got AWS, you've got Azure, doesn't matter which cloud it is, and you've got your data center. And you've got containers that are running in all cloud providers. So I have containers. And we need the containers to scale in, to scale out, to update, to not update. So let's pretend right now we use the Amazon Kubernetes service, which is a great Elastic Kubernetes service, which is great. And if we use that as a control plane, it would manage the containers in AWS, Azure, and our data center. All great. All of a sudden, everything's great. Now, all of a sudden, AWS has a hacking event and network failure, and they're no longer there. Now we have no control plane for the containers in AWS and our data center. And what this ultimately means is we can't add capacity, delete capacity, do anything until AWS comes back on. So if we did that, we'd be architecting a single point of failure in our multi-cloud environment, no matter how good it is. So typically in this environment, what we'll do is we'll have to use Kubernetes. We'll have to put Kubernetes servers in each cloud. And either we can manage our own, or we can use something like IBM OpenShift, which is via Red Hat. And OpenShift is a container management platform we could put in all clouds. It's kind of managed like by IBM Red Hat. So much of the heavy lifting is done, but you can put it in all clouds. So now if the Azure cloud went down, it doesn't matter, because you've got the same thing in all clouds. AWS and your data center can keep up and running. So, you have to look at which type of a Kubernetes deployment you're going to do. Obviously, some are more complicated than others, but if you hit the ease in your architecture, so we have to be fairly careful about how we do these things. So Kubernetes automates container deployment, scrolling, management, auto-scaling, that kind of thing. And it's got a control plane and it's got a data plane, just like pretty much every other thing that we're actually going to be talking about. We're going to have a Kubernetes control plane that's going to do its thing. For example, we've got this Kubernetes control plane over here. And this is going to be the control plane. You typically think of the cube supervisor as the control plane. There's typically the etcd that's part of your control plane. There's typically a controller manager, and you typically have a scheduler. Now, this is the control plane. And then we typically have the nodes where these things run. And in node, we'd typically have nodes where things run, and we'll have maybe multiple nodes. But in each node, what we'll have is we'll have the pod itself, and in the pod, we'll have the container images. And we'll have the kubelet. So, we typically have these two elements in a Kubernetes. We're typically talking about the control plane and then, of course, the data plane. So securing Kubernetes or any other type of container orchestration platform involves, using cloud providers tools like IAM, hardening any services or virtualization or any services that we'd have, or the servers that would be running them if we run our own. Patch and update components of our Kubernetes master nodes, our nodes, control plane, data plane, forwarding plane, what have you. Implement a robust security policy, good, strong network security for consistent protection. Use benchmarks and tools. Follow the Center for Internet Security benchmarks. So use stringent standardization and scanning tools to check the code and make sure these are good. Create a secure image repository and make sure only people with the right access can get access to it. Think like role-based access controls, principle of least privilege. Scan those images, make sure they're good. From a configuration perspective, we always want to start with robust, secure defaults for our containers and hosts. Then we want to harden the host operating systems, encrypt our data, encrypt our storage for our storage security. Our network security, we want to use network segmentation, routing controls, firewall rules, monitoring, and even the images. We want to validate and assign them whoever's building them as part of the CI/CD process. So for secure artifact repositories, we want to really be able to trust and verify the content in there. We need to be able to enforce mechanisms like digital signatures to ensure authenticity and integrity of the container images. Really strict access control, because we only want authorized people to be able to push or pull images from the system. We want to routinely check our images for vulnerabilities. And we need to make sure that our container images are immutable and they haven't been changed by anyone. And then we need to make sure we've got good documentation, of course, scanning these images in what way along the line. Best practice for repositories: use only secure sources, sign and verify images, confirm authenticity with a digital signature so we know where it's coming from. Scan everything before your deployment, vulnerability scan it. Regarding access control, really restrict who can push and pull. Keep an audit trail, regular updates. Are these starting to sound familiar for almost everything we say? I hope so, and there's good reasons for that. So kind of keep that in the back of your mind. We will also need to come up with some runtime protections for containers. For example, we want to be able to look at real-time visibility in the containers to be able to look for normal and abnormal behavior. We want to be able to log and audit things that are going on to make sure that we can catch things when they're occurring. We want to micro-segment our containers so they can't talk to each other, to, again, segmenting the network. And ideally, we can use some container-specific firewalls along the way to filter out network traffic. And we want to come up with systems that have the ability to, in some shape or form, provide an automated response to various threats. Now, okay, these serverless functions, remember, they run on somebody else's server. We're uploading your code, they run on their server, we have no idea, and then we pay for each time it runs, or a number of times that it runs. So I'll give you the Cloud Security Alliance definition of serverless, and they say serverless computing is an execution model where the cloud provider allocates resources on demand. Payment follows a pay-as-you-go model where based upon actual CPU usage or server invocations. Here's the thing. You pay every time it runs. So serverless is not serverless. You don't have to think of the infrastructure the cloud provider does. And they tend to be fairly simple. And the reason people like it is developers supply their code and the cloud provider handles all the work, the heavy lifting, the infrastructure, the maintenance, the scalability. So this kind of Azure function, Lambda function, Google function, function as a service is typically out there. Now, what'll happen for most of these serverless activities is we're going to make it an event driven. If this happens, then do something else. That's event driven. So we'll typically define a function, or the developer would, and then a trigger. Somebody puts something in an S3 bucket. They set the wrong permissions to public. It's not, and then a Lambda function kicks it off and remediates it to private. Those kinds of things. So most of this security work here is going to be on the provider, but the developers still have to secure their code, manage their access control, or whoever, and somebody's going to have to manage their access control and protect the sensitive data in transit. So if we really think about it, we're always dealing with the same kind of technology. We're all dealing with servers, virtual machines, containers, or an environment like this. Now, with serverless, because we have less control over what we're actually dealing with, what we're really dealing with is IAM. That's one of your bigger things that you can deal with for serverless, because it's running on somebody's system. Don't know what these systems are. You may not even know what the IP addresses of the systems are. So what do we have? IAM. So use the principle of least privilege, grant only the permissions needed for the function to do its job. Get very fine-grained with your access control and precisely define which functions or resources are going to be needed. Use context-aware authentication. So we want to base permissions on real-time factors. We don't have a lot to do that we can use, so we better get real good and determine use as much security as we can. So maybe user, device, time. We want to be able to use immutable infrastructure and secrets management, because if anybody can just upload the code or change our code, look what they could deploy. So we're going to be using immutable infrastructure, meaning we're going to put an environment where it can't be changed, like object storage, immutable object storage anyway. And secret management, we're going to have a secure environment for any secrets, passwords, database strings, anything that we need. We're going to avoid hard coding any passwords or API keys into an environment. We'll use an environmental variable. We'll use services to manage our secrets. So AWS has a secrets manager. Azure has a key vault. The key here is you can store, retrieve, rotate your credentials in a secret, secure environment. If we have secrets, they're only as good as nobody knowing them. So we want to rotate secrets periodically. So if you have a password that's good for 90 days and somebody guessed it on the first day, they can use it for the next 90 days. So by rotating them frequently, we reduce the risk of a compromised credential. We want to make sure that we use IAM roles to restrict secrets to only authorized entity. And whenever possible, we really want to use that zero trust model. Let's talk a little bit about securing AI workloads. So we're now in a world where AI, generative AI, machine learning is part of everything. And there's a lot of things that go on with these systems. One of the primary components of these systems is a lot of data. So AI workloads typically involve large data sets, not always, but typically take significant compute power, especially things like an LLM to create, and other specialized hardware, whether it be a graphics processor, a tensor processor core, or some other kind of device that can actually go through large amounts of information. Now, we can do this in the data center. We can do this in the cloud. In the cloud providers typically have a large amount of compute capacity, which we could just use on demand. Of course, we're going to pay for that, so we can also run it in our data center. So we have the ability to run in each place. The key here is with AI and AI workloads, they can improve our customer experience. They can help us make better predictions or inferences so the business can better invest in certain things. AI could help the business innovate. AI could help with so many things. Now, it doesn't mean we use AI everywhere. It means we understand the business needs, and then look for ways that AI could make it better if it could. And if it can't, we don't add the AI there. But if we look at AI, there's a lot of risks that are associated with it. So we may be using a large language model where we train it on a vast set of data. We could be using a small language model where we train on a smaller set of data. But we got a couple of things that could happen. So if we've got a model and somebody manipulated that model, that would be a problem. If somebody poisoned our data, that would be a problem, and our data would change things. Whether we run the risk of sensitive information disclosure. What if we had a custom model and somebody stole that model? So there's a lot of things that we can actually deal with that we need to actually address. So model manipulation, for example, this would be an attempt where a hacker would trick the LLM, the large language model, or whatever model we're using into producing inaccurate results. So an adversarial input or something completely wrong. Imagine a business doing something based upon bad data because the model was manipulated. Same thing with data poisoning. Somebody injected false or biased data into the training data that was used for AI. Now, this means the AI can do some pretty horrible things. The models will be using incorrect data, produce skewed or incorrect predictions. If the business invests in these predictions, they can get in a lot of trouble and have a lot of problems because they could be bad predictions. We always worry about sensitive data disclosure. We worry about the systems kind of being able to reconstitute information and leak information. We also worry about unauthorized exposure or leakage of personal, proprietary, or confidential information. And this could be a privacy breach or even a security incident if it occurs. We worry about the model's theft or its distillation, where we've got unauthorized aspects to the access, and somebody replicates the model's architecture and parameters. And that could steal someone's intellectual property or other things. So lots of problems that can exist here. We can also have model failure. So we could have a bug, a hardware issue, a hallucination, which causes a degradation in service and very inaccurate information. We could have an insecure supply chain along the way, too, where we have vulnerabilities that were introduced by third parties in our LLM ecosystem if we're using a large language model. And this could involve compromised software libraries or hardware, things that don't do things right. We could potentially be using insecure application plugins, which will pose all kinds of security risks, especially if they interact with our LLM. And that could include unauthorized access or privilege escalation or even tampering with input and output. Of course, we run into the risk of a denial of service attack where something basically overwhelms the LLM service that we have with excessive requests or malicious traffic. And that means downtime and the services won't work or something to that effect. We could lose governance and compliance as well, where we can't meet regulatory issues if somebody exploited our systems. So these are all kinds of generative AI challenges we have to deal with. So that means we're going to need robust measures integrated into any kind of security program. Constant risk assessments, threat intelligence, proactive mitigation strategies. And for every unique LLM we have in generative AI employment, we're going to have to truly understand it and provide whatever is necessary. So we've got some categories, especially according to the Cloud Security Alliance's terminology taxonomy, if you will. And they consider them to be data assets, the LLM operational environment, the model, the orchestration service. And at least in this world, they have a bunch of stages of the actual life cycle, which include preparation, development, evaluation, deployment, delivery, and then service requirement. But we have to account for all the assets and all the life cycle changes so that organizations can formulate an end-to-end security strategy that will address the weaknesses in generative AI or LLM systems. So let's talk about the responsibilities. These are complex ecosystems we're going to be dealing with, AI and machine learning. We're going to have lots of actors, providers, technology vendors, services, and each will have distinct responsibilities in the AI supply chain. Now, this is going to be a shared responsibility model, just like cloud computing. AI providers and consumers will likely share different aspects of security. It's going to be important to clearly define which parties are going to handle which responsibilities. And that way we can have safe and effective strategies. So some thoughts to things to think about to mitigate some of the risks in AI. From a data security perspective, we have encryption to protect our data in transmission and its storage. What we can have is something called a differential policy, and that adds some controlled noise so that individual records cannot be tracked back to a person. We can do some kind of secure multi-party computation where we process data from multiple sources without revealing sensitive information. But in order to do that, we use something like anonymization or tokenization. We can do confidential computing. We can use trusted execution environments to safeguard data and AI model execution. Now, when it comes to the models themselves, we really want to try to harden them and defend against adversarial attacks. We want to enhance the model's resilience. We want to be really careful with training. We want to be very careful with the techniques that are used to training to make sure we don't do things like to improve generalization and reduce any kind of errors that you would actually have in the training system. We need adversarial training. So typically in an environment, we have two systems, a primary system and an adversarial system, and they typically work together to make sure there's no bias and the model is accurate. We might want to watermark the model, where we embed unique identifiers and asset ownership in the models to deter someone from stealing our model. And we might even want to do some output manipulation, where we can alter the responses by AI to obscure the decision-making process to make it harder for attackers to kind of guess or replicate the state of the model we have. When it comes to securing the infrastructure, for GPUs and TPUs, we're going to basically keep them on virtual machines. We want to make sure the virtual machine's firmware is updated, the GPU's firmware is updated, and we've got as much network security as we can use. For AI services, we want to follow the cloud providers' best practices, including whatever they would suggest, like strong access controls and continuous monitoring. We want to implement quotas and rate limiting to implement the measures that we can use to detect or prevent something crazy like a DDoS attack going on where the volume goes up. And of course, we have to be careful with our supply chain. So we will have to define and approve a cybersecurity policy for the supply chain. We'll have to look at the software and supply chain risk management, where we're getting it. We'll regularly audit and update third-party dependencies. We'll be vetting third-party services and conducting security assessments before even extending services or working with people. And we're going to be dealing only with trusted sources. So we're going to make sure that we get software from dependable sources, and we'll maintain an approved list of sources that we'll be looking for. Okay, we are back. So does anyone have any questions? Hope everybody's having fun with all this cybersecurity. We even talked a little bit about AI security. So I hope everybody's having fun, as long as I know I am. So hope I was having a good time. If you have any questions, let me know. Drop them in the chat box. And if not, we'll continue to go on. So just let me know if you have any questions. While I wait, just in case you joined us, because we never know what time people actually join us on YouTube. They pop in and out at all times. We are on day 4 of the CCSK Certificate of Cloud Security Knowledge Training course that we're running. You can go back and watch the previous 3 days if you want, and my team will drop the links in the chat box for you, just in case you didn't know. You can obviously watch today and then go back afterwards. Just want you to know that you have access to the other days. Also, there is a completely free study guide, set of cheat sheets, if you will, and my team has dropped that into the chat box link and is also in the description of this video. So you've got lots of resources to help you prepare for the exam. Now, I don't see any questions popping in, so either I'm doing a really great job answering questions, and thank you so much, your favorite teacher. I'm so deeply appreciate that. So either I'm doing a great job or people are being shy. So don't be shy. If there's ever a question you go through while we're here, I really do want to help you. And I'm here. And if not, give me a hashtag CCSK so that I know you're still here. You're having a good time. You're awake. You're alert and oriented. And then I guess we'll get back to the content if there's no more questions. Okay, we're going to begin Domain 9 of the Cloud Security Alliance's Certificate of Cloud Security Knowledge, CCSK, exam preparation. And in this section, we're going to be covering data classification and data security. And we'll begin with data classification because in many cases, we need to know what we're protecting before we think about how we're going to secure it and provide the right level of security. So the first thing we have to understand is that data is an asset. It is something very valuable to the business. And it can be used to help the business make better business decisions, for example, and forecasts, for example.
Data will be the source of truth for all the artificial intelligence systems. If the data is bad, the AI is going to be bad. And it's going to be critical for an organization to have clean and accurate data in modern business. So we're going to talk about some roles and ownership type roles and custodian roles at some point. And the reason we're going to talk about this is internationally, there are going to be some laws. For example, the GDPR specifies that certain data type people are in place. So we're going to come up with some academic definitions here, but that's because you may need to know things that are similar like this from a regulatory perspective. And then you can compare and contrast whether what's used in your country or jurisdiction is similar terms, but at least these are more generic. So we have to begin with data ownership. And there's somebody that owns that data, right? And that person can determine who can do what with that data. They're the one that can honestly assign the responsibilities. So the data owner could be the CEO if they own the business and they own the business's data. But we have to be careful with that. And there's other definitions of data owner, but we have to think about who owns the data. Only they can delegate or assign responsibilities to others. And these roles that will exist in an organization could be defined by the organization, or they could be specified by laws, regulations, and other contracts. So we're going to talk about some common roles in data ownership and the data owners and the such. So the owner, for the most part, is the organization that collects or creates the data. And there's typically a specific data owner inside of the organization. And that could be a department head or a business unit manager. So if you've got an enterprise, for example, and they've got 5 different kinds of business units, an auto business unit and an airplane business unit, the data owner for the airplane business unit may be the president or whoever's running that. And you may have a different data owner for the car unit. And then you may have a different somebody that owns the actual business. But typically speaking, that's what we're talking about. In the cloud customer is typically the data owner. So if company XYZ is the data owner, they're the one that has the account, they're the data owner. Now, there's other ways you can actually look at this. The next type of data role we're going to talk about is a data custodian. And a data custodian is someone that works and does daily maintenance on the data. You know, when you pick a custodian to care for someone, they're kind of that person that gets to help that person do their things every single day. Well, a data custodian is the person that works with it. And whatever the data owner determines is necessary from a security perspective, the data custodians will handle the data with regards to that care at that level of security that's necessary. So a database administrator inside of an organization that's working on the database as a data custodian, because they're working with that data even if they don't own the data. Now, the next type of role we have in data ownership is something called the data steward. And this ensures the data's context and its meaning and that people can actually understand what's coming out of the data. And this helps the organization use the data properly. So if you think of the data steward as someone that kind of makes heads or tails out of the data, that might help you get through this. Now, we may have something called a data processor. And a data processor is going to be any person who manipulates, stores, or moves data on behalf of the data owner. This could be things like copying the data, printing the data, destroying, or even utilizing the data. And in international law, the cloud provider is typically considered the data processor. So a couple of more key points on data ownership and custody. A data processor does not always have a direct relationship with the data owner, meaning it could be a third party or a supply chain. So we could have a data here be partnered with another company, and they could be a data processor using some of the data. Now, the data owners, by comparison, are the legally responsible people for their data, as they own the actual data. And the data owner is going to be responsible for the data if the data is compromised by a data processor or anywhere else in the supply chain. Just like you, if you have your data in your data center and it gets hacked, you're there for the regulators. If you get hacked, if you're in the cloud and you get hacked, you're responsible for it. If you're on the cloud and the cloud provider gets hacked and that causes your data to be lost, you're still responsible for it too. And that's the key to understand data owners. Even if third-party providers make mistakes, you're still responsible for it. So we'll talk a little bit more about ownership and custody. And this is going to be a little bit specific to the data in certain circumstances, but ownership is different than the people that are working with it. And with regards to systems owners and data owners, they might be a little different. The cloud providers own the underlying infrastructure, so they're really the system owner. Because remember, cloud computing is a rental business. They're the landlord, and you're a tenant renting space in their environment. But the system owner isn't exactly necessarily responsible for the data on the systems. That's the data owner. Goes back to the same thing. Cloud provider accidentally deletes your data or exposes your data, you could still be legally responsible for it. Now let's talk about, from a data categorization perspective, let's talk about the data owner's role. And this is going to be best positioned to understand the data usage. This person is going to be responsible, typically speaking, for categorizing the data. And with an organization, we can come up with any number of categories or types of data when we classify data. And we can have a category that could be clearly defined, or we can have a category that somebody arbitrarily assigns some data owner. So let's talk about the drivers for categorization. Well, for one thing, it's regulatory compliance. Different regulations govern different business activities. Categories may be based on regulations or requirements. For example, GDPR may have specific requirements in Europe, or SOX compliance for financial institutions and publicly traded companies, or HIPAA compliance for specific privacy issues in healthcare and whom can speak with whom in healthcare, or PCI DSS. There's lots of reasons businesses have to categorize their data or determine certain things to meet a regulatory compliance. But organizations could also categorize their data based on, say, business function. Billing, marketing, operations, finance. I mean, they can categorize it that way too. Businesses could also categorize their data by functional unit. So what if we had an international conglomerate? We've got an airplane engine department. Okay, they may have their own data and classify their data. We may have a train department. We may have a healthcare department and things like that. We're going to have different functional units, and that might be a way to categorize the data. Because we have to come up with some structure. We can't just, if we're going to categorize things, we can't have everybody categorize it their own way. We could also categorize our data by project. Okay, so we've got a new data set per product per project, and then we therefore categorize it that way. But whatever we do, however we want to categorize our data, it has to be consistent again and again to make it easy to understand and easy to secure. Now, who's responsible for the data classification? Who's ultimately responsible? The data owner. The data owner is going to be typically responsible, and they will be assigning activities to others. Let's also talk about categorization of your data. Not all data is the same. Some data, if it gets out, is not really harmful. Some data, if it gets out, could destroy a business. The secret formula for the new billion-dollar drug, the secret formula for the next GPU or the next quantum computer or something like that, or a battery that just never runs out of energy. So one of the ways we can enhance our security is classifying based on sensitivity. Classified, very sensitive. Unclassified, no big deal. And there's lots of contexts and ways we can do that. We could also classify our data based upon jurisdiction. Maybe we have privacy laws where we can't take data out of a certain environment. And if that's the case, that is okay too. So we categorize it that way, and we protect certain parts of data that are moving along the way. We could also classify our data based upon the criticality of the data. How important is the data for the organization's long-term survival? And this would be determined when you do your business impact analysis and you quantify your assets and you understand the business. And that's why for us architects, we have to understand everything we're dealing with, what's critical to the business. We could also classify data if we wanted by organizational policies. And we can come up with a classification level. We can assign specific responsibilities and roles. And, if we think about data governance, This is the kind of thing we're going to have to do. We're going to have to come up with a policy. We're going to have to be very clear about who can do what. Now, I'm going to talk about data mapping here. And the purpose of data mapping is to ensure that if we have data that's going to be shared in between organizations or departments, it's normalized and it's created in a way that's going to provide mutual understanding. Now, let's talk about the context of classification. It's going to be essential to recognize and protect sensitive data across different systems or organizations. And this is going to make sure we don't expose any kind of classified data outside of the world. Now, how do we map our data to these classifications? Well, there's lots of ways we could do it. We could do it manually. We could do it in an automated manner. And there's key technology we can use during data lifecycle. But we can do it in a manual way, we can do it in an automated way, and we can do it in a hybrid way. But every time we make a decision, each thing will do one thing better and another thing worse. So there's lots of things that we need to think of. When we start thinking of key considerations, we have to maintain data for classifications and labels when we map it. We also have to ensure that the security controls and the oversight are going to be preserved when the data is used in its different contexts. So we're going to want to label this data. And, data owners label the data after they categorize it and classify it. Now, a label should indicate maybe the office or the role of the data owner, but not names. So you're trying to make it easy to understand what you're dealing with, to understand the sensitivity, but not put things that could ruin privacy along the way or give too much information to other people. Now, if we're going to make labels like anything else, we have to be consistent. So we have to come up with something that's going to be enduring, understandable, and consistent. We may want a hard copy of data where we've got printed headers and footers of data, for example. We may have electronic files and we embed in the file names, or we add metadata to the data so we can understand the label. And these kind of labels can include things like, when the data was created, when the data should be destroyed or scheduled to be destroyed, the confidentiality level of the data, access limitations of the data, and so much more. This is really where you're going to make it clear what you're doing with, so then you can set a policy on these types of data based upon sensitivity, criticality, what have you. So part of data management is really to think about tools for lifecycle and security controls, such as data loss prevention systems. For example, so if data is critical to us, we need to make sure data doesn't leave our environment. So we have data loss prevention systems that we could potentially do that could potentially check things. And I'll give you an example of what some of these things could be. One type of it was, if this, for example, is say the internet, and this is your internal organization, we can do what's called egress monitoring, and we can monitor along the way going out to the internet with a data loss prevention system. And what's going to happen here is this system's going to look and say, is data trying to leave this network? And if so, is it sensitive? Don't let it. So that's one type of a system we could do. There's also data loss prevention systems that we could even put on the host itself. So let's say this is a server, for example. We can put a data loss prevention system on it that will keep data from leaving the server. We can also, with that same system, we could disable USB ports, for example. And by doing that, people can't plug in other things. And honestly, there are some companies that are so crazy about security because they need to in their business that they will physically break the USB ports on these servers themselves so people can't use it, or unwire them from the motherboard depending upon how the systems are set up. But data loss is critical, and it's going to be critical to make sure that we can protect our data. And labeling our data, for example, will make it so much easier to do so. We have to understand from a security architecture perspective, from a cloud architecture perspective, from an enterprise architecture perspective, the flow of the data through the system. We need to know where the data sources are coming from. We need to understand the data controls that can exist. And this needs to be documented. It's usually in a diagram, but usually a diagram plus explanation is really what's necessary. Understanding the data through the system is critical. You can't protect it if you don't understand it, and you can't block stuff if you don't know what you're blocking, because you could break the environment. So we're going to talk a little bit about data discovery, and sometimes we have to find out and inventory what kind of data that organization even has. And this can involve an initial data inventory, an electronic discovery, or even data mining to try to figure out what we have. We could use label-based discovery of our data. And if we have good labels that were created by the data owners, it's going to make it very easy to do data discovery. It'll help determine the types and the amounts of data that need to be controlled. So we can use like a utility. So realistically, we can facilitate a response to specific mandates, like a court order or regulatory demands. And this is going to ensure accurate collection and disclosure of relevant data. And that's the utility of this. Sometimes we have to do this, provide certain amounts of data, and we can do this with this type of discovery. We can also do metadata-based discovery. Remember, a lot of times with data, you'll have additional data about it or metadata. And when we talk about object storage has a whole lot of metadata, which is information about the data or data about the data. So metadata-based discovery can be quite good, and especially in object storage, we can do a lot more of it. But it's mining that data to the data. And, when we're dealing with this, metadata can be scanned, it can look for specific terms and collect matching data. Now, that's only going to be good if the metadata is accurate and it's labeled correctly. But if it is, we can figure out a lot of the data based upon the metadata. We also have what's called content-based discovery. Now, this is what you do if the data that you have has no metadata and no data levels, and this involves delving into the content of the data sets. So basic term searches, sophisticated pattern matching technology to identify certain types of data. So this is getting more complicated because we don't have the information in the first place. Now, data can be structured, semi-structured, or unstructured. And I'm going to talk about what those are. Structured data is sorted according to meaningful, discrete types and attributes. Think of a database, rows and columns, or a spreadsheet. That is very structured data. It's what you'd find in those relational database and databases. It is very easy to perform data discovery because it's organized so well. Structured data. By comparison, we can have unstructured data. And this is going to be unsorted data. It can have a tremendous number of content. Unstructured data could be a picture, a video, an audio, and a PDF, all in the same folder that we want to look at. So this is going to be much more challenging from a data discovery perspective because it lacks inherent structure. It can be done, and AI can help us a lot with this, but still understand it's going to be harder. And then we have this concept of semi-structured data. And here we may have some tags or elements that's going to give us some information. It doesn't require a rigid structure, but it's not unstructured. So it's semi-structured data, and that's not that challenging to work with by comparison to unstructured data. We may also have to think about the data locations and on data discovery. So, for example, we may have a law related to data sovereignty. Data sovereignty may mean your data must stay in a certain country. So we might need to make sure that our data is not in the wrong country. And we have to understand that because if there's a data sovereignty law and our data is in the wrong country, then we could be facing, some kind of regulatory fine or what have you, or more. So we have to think of these laws and regulatory challenges, and we have to understand where our data is going to be and protect against it. So let's talk about some of the challenges we might have. So unstructured data or certain services are going to complicate things because it's not structured. Now, the location of the data can also affect costs, especially if we're dealing with ingress and egress fees of cloud providers in certain areas. Structured data in databases are going to be very easy to discover. And unstructured data, free-form text, is going to take a fair amount of complex queries. And that means it increases the risk of missing data or incomplete data. So let's talk about the data locations and understanding that. So we have to know where the data is stored. It's easy in our data center. We know exactly where it's stored, the building that we're in. In the cloud, just because we put it in a data center, our availability zone doesn't mean it won't be replicated to many different places. So we have to understand that when we work with our providers. And we have to align our data discovery goals with our data characteristics. So let's talk about designing and securing data discovery. So we have to consider data usage and data analysis methods. We have to design the discovery process that's going to meet legal, technical, and organizational needs, because we don't want to break any laws when we're trying to discover the types of data that we actually have. So let's talk about analytic systems and their role in data. So we've got a lot of data. It's going to be very hard to get through some of these systems. So we have data analytics systems, and we can create new data from existing data sets in an automated way, in a semi-structured way. And there's a lot of systems out there that can go through, that can mine data, that can do data analytics. And that's kind of the basis of the original machine learning, artificial intelligence we've used for many, many years now, to try and basically pull information, mine the data, and make inferences or make heads or tails out of the data. So I'll talk about data mining, and that really encompasses various data analysis activities. It utilizes these big data capabilities that you're typically talking about. Cloud providers have great big data capabilities. And realistically, we're talking about the speed of the data, the amount of the data that's all coming in with big data. But that's beyond this. That's more for a data architect role. But keep in mind that mining through the data is going to be very critical. Now, part of what we're trying to do in this world is basically getting real-time analytics. And we can honestly, in some cases, get actual information from the data in real time. As soon as the data is created, we may be able to look at this. And these kind of things work in a semi-automated manner, but there's lots of different ways we can be getting data. We could be getting streaming data from, say, a Kafka environment and running real-time analytics on that. And of course, the cloud providers have their versions of that as well. But we could be looking at real-time data, but we can also be doing real-time analytics, or we can be doing real-time analytics as the data gets stored and potentially keep giving us better information as well. The goal of this is all business intelligence. And business intelligence is going to use this, all these information is going to keep going back in your data. And by understanding the data, it helps people understand the business much better.
Okay, we are back. So hope you've all been having fun with this cybersecurity training. I know I have. I know I enjoy anything related to, say, networking or security. It's just something that I've always absolutely loved. So we're going to break and see if anybody has any questions. And based upon the questions, now's the time to ask them. I'll do what I can to answer them. So instead of an OS-K8 control plane on all clouds, can we use K8 services on respective clouds? So what we have to understand is when it comes to Kubernetes, we're going to have a control plane and we're going to have a data plane. So let's look at realistically speaking, you're going to have two architectural options, because I'm not sure which one of these options you're actually referring to. So bear with me. So let's look at this. So let's have two situations. So let's say we've got containers on AWS. Let's say this is AWS. Let's put some containers that are running here. So let's say this is a finance application, and let's say this is an accounting application that are running in containers. Probably not a finance application, but let's just pretend it was. So let's say this is AWS. And now let's say we have this in Azure. Bear with me. Let me go fix my screen. Somehow I zoomed into it to see something. So now we have AWS. This will be Azure. while we're at it, let's make this one Google. So the control plane is responsible for a lot of things. I'm going to put the control plane up here for right now. It's not, but I'm going to put it here just to illustrate it, and then we'll talk about our options. So if we have our own control plane, and our old control plane is made up of some servers that are in AWS, and we've got some some of our own Kubernetes servers sitting in Azure, and some of our own Kubernetes services that are all part of this control plane sitting in Google. And I've got all the right kind of networking between us. So what's going to go on here is, let's say we need to have 5 containers running on the finance application in AWS. And if one of the containers crashes, the Kubernetes control plane will basically say, spin up a new container instance. And that's where Kubernetes becomes self-healing. Now, all of a sudden, we've got this accounting application and it needs more capacity. Well, we can use auto-scaling with Kubernetes where it adds more containers. So all of this is great. But if we have our own control plane in 3 clouds, let's look at what happens. So, and this means we manage it ourselves, or the control plane that we can be getting could be, say, IBM OpenStack, which we could use across all clouds because it's not proprietary and it's managed. So if we have our own control plane and AWS goes away, we don't care. And why don't we not care? Because if AWS just has disappeared, the control plane that we have running in Azure and Google can still add capacity. So if a third of our capacity from AWS is lost, it doesn't matter because we'll just add capacity on Azure and Google. Let's bring AWS back into this. And in this particular, so think about this. So if we had AWS Elastic Kubernetes service that was running in the control plane for AWS, and AWS went down now, well, now Azure wouldn't have a control plane to expand its containers in or out, and neither would Google. Neither one would. And the reason that would is because the control plane that would be on AWS would have gone down. Now, it doesn't just have to be AWS that could go down. Everybody goes down. So, AWS is an extremely well-run cloud. They don't go down that often. They go down. Azure's a well-run cloud, and they go down too, and so does Google. So we always have to think about what happens and where are the weaknesses in the system. So we can run the same Kubernetes control plane across and have our Kubernetes servers and our control plane across 5 different clouds, data centers, and everywhere in between. It's only when we use the cloud provider's managed services that if anything happens to that cloud provider, we lose the control plane in our other cloud providers and data centers. So we just have to be careful about that. Hope that made sense. And that way we're always free to go from vendor to vendor, data center, cloud. There's no changes. We don't have to think about anything. I don't see any other questions yet. So either we're doing a really good job explaining things, and if so, I'm really happy about that because that's my goal. I try real hard to. Or you guys are being shy. So just don't hesitate to be shy. I want to make sure this is a great educational experience for you, that you all increase your knowledge and you develop those skills that are going to help you get to your goals. So please don't feel free to ask any questions. And if not, we'll go back to the content. So I want to know that you're there, and hello to all of you that are out there. We're so happy to see you here. Before we get back to the content, I would like to say a few things. One is, if you're enjoying the content, please give it a like. If you're not a subscriber to our channel, please subscribe and hit the bell to be notified of new videos to assist you in your architecture career, whether that be cloud architect, security architect, AI architect, enterprise architect, or any networking or any architecture career for that matter. And at this point, I want to remind everybody, if you just joined us, that we have a completely free e-guide that goes along with this course. Please feel free to download it. And maybe give me a hashtag CCSK, or a hashtag Certificate of Cloud Security Knowledge, or a hashtag CCSK V5, or a hashtag CCSK certification. So I know that you're awake and out there. Chris, I think we should get back to the questions. I don't see any other questions coming in. So let's get back to the content. And if anybody has any questions, just let us know. We'll do anything we can to help.
Now we're going to discuss cloud data security. And the first thing I want to talk about is the cloud data lifecycle. So in the cloud data lifecycle, it's going to be from the time the data is created to the time the data is destroyed. And there's several phases along the way. The first thing we're going to do is we're going to create the data. And the data will be created. Now, creating data, if we don't use it, is going to be meaningless. So we're going to use the data for something. And we're done using it, we're going to store that data. And maybe we need to share that data with other members of the team. And at some point after the data has been shared with others, and we're no longer actively using it, we're going to want to archive the data. And archive will be long-term storage. And typically there's reasons to do this. You could have your active storage in very fast, expensive NVMe hard drives, and your archival thing could be a RAID array of magnetic storage, traditional old school hard drives. And it's cheaper to keep data on those than it would be an NVMe drive. So that's another reason why I would archive it like that in the data center. Now, on the cloud, we typically use object storage for data archival purposes. Think AWS S3, Google Cloud Storage, Azure Blob. And all of them have storage tiers that are active where you pay more to use it and get access to it easily, and you pay much less to keep it stored long term. And that's what we're talking about. We're talking about archiving data. So, for example, Google S3 would be the traditional object storage, but we would put it on Glacier, Amazon Glacier, and that would be lower cost archival type data. And we're going to do that in everywhere we're at to keep our data costs low. And then when that data is no longer used for us, first, there's no point paying to archive the data and keep it archived anymore. But also, we don't want that data to be used against us. So we're going to destroy that data. And maybe we use crypto shredding. If it's on hard drives, maybe we would drill holes in them, burn them, whatever you want to talk about. But we have to destroy that data so it can't be used by others to harm us. So we have to think about where the data is going to be created. Is it created in the cloud? Is it created on premises and sent to the cloud? Is it created in some wacky remote location that's going to be really hard to get to and really hard to access the network? Is it going to be in other clouds? But we always have to think about where it's created. And is it in an environment where maybe we've got to use it? We have to always think about where it's going to be created. So let's talk about the create phase. So let's assume it's created in a remote data center. Well, if it's created in a remote data center, we're going to have to encrypt it before we upload it to the cloud. And we, realistically speaking, want to use some strong encryption methods and good key management systems. So you could think about secure network transfer using, say, TLS security, maybe over a browser, for example. Now, if the data is created in the cloud, it's pretty easy. We want to just encrypt the data as it's being created. And this is going to protect against hackers, for example, and even the cloud provider stuff. Now, the key management obviously is going to be critical for maintaining your encryption security. Now, when we store the data, we have to describe the handling immediately after we create this data. So some key security controls here are to provision access rights for your storage locations, ensure storage locations are properly secured, protect data through encryption at rest when needed. So we really want to make sure we're encrypting our data. Now, data in use, let's talk about the complexity of that you have in the cloud. Different cloud environments offer various interfaces, web applications, APIs, or services. Hybrid clouds may be transferring data through multiple methods as that data is being used. So we have to secure the data, and here's where we need to understand specific uses of the data and data flows inside the organization. We need to secure every data transfer, and there's lots of ways we could do that. We could have a private line between the data center and the cloud, and we could actually run an IPsec on that, which is going to encrypt that whole link. And we could still encrypt the data with TLS security as a second form of encryption. Or we can encrypt the file long before we send it, and then send it with TLS encryption, and then send it with IPsec. So there's lots of ways that we can secure the use phase, where the data, when the data is moving in a data transfer, if you will, protect data each storage location, transit. And the more your criticality of your needs are, the more you might think of different technologies to protect it. Now, there's always going to be operational aspects when you're using things. So secure platforms you are going to want to use to connect to the cloud. Because if you have a unsecured data center and you connect it to the cloud, your data center could be an attack vector into the cloud phase, or vice versa. These things can occur. So we're going to have to deal with, when the data is used. If we're dealing with people and bring their own devices and mobile devices, we're going to have to secure them as well. Now, here we're going to get involved pretty heavily in rights and role management. Data owners should classify, protect, and oversee the data as it's being used. They need to restrict permissions for modifying the data or processing the data and keep it restricted to only essential functions. Again, we always go back to the principle of least privilege with everything we do. If you don't need it for your job, you don't have access to it. So we want to maintain good logging and audit trails for any kind of data transfers or manipulations. Now, there are global collaboration risks. Because if we start collaborating and we have big networks all around the world, all of them could be used to attack us as well. And there's other things to think about. So whatever we do when we share, we have to make sure we've got good, strong security controls and keep them at all the time. We want to utilize security measures from the previous phrases, encrypted files, encrypted communications. We want to implement potentially information rights management solutions to protect certain types of information that we have. We want to use good logging and good permissions so we can really control access and keep track of access. Now, during the share phase, I want you to be understanding and concerned about jurisdiction and legal requirements. You may, and the reality is you have to craft any kind of sharing regulations that you have based upon legal environments. So if you're going to create a sharing restriction inside your organization, it needs to be based upon the laws. Because certainly, like I talked about earlier, data sovereignty, you may not be able to send certain data onto a certain part of the world. And because of this, we need to limit or prevent data transmissions to certain locations to stay in line with either a regulatory environment or a contractual obligation we have with a provider or someone else that we negotiated along the way to do business with a third party. We need to understand import controls, export controls to all regions where data may or may not be shared, because otherwise we don't want to commit any crimes by accident. Now, in the archive phase, we still want to check other things like egress monitoring to make sure the data is not leaving our organization. And long term, we need to really think about data security over an extended time frame. Because if they're going to be somewhere for a while, we need to make sure that while is properly secured. Now, here's where we're going to typically be using some good cryptography. And we want to make sure that the crypto system that we're using is going to be resistant to current attacks and future attacks. For example, there was a type of encryption called DES when I was much younger that we used to use, digital encryption standards. But that became insecure as compute power got stronger to break it. And then it became triple DES where we encrypted it 3 times, and then we've moved on to bigger things. So if we're going to archive something, we need to know what we're going to do is going to work from a security perspective. Now, if we're using encryption, the key to decrypt the data is the encryption keys. The key to encrypt it and the keys to decrypt it. So we have to make sure that we keep the right keys. If other people get access to their keys, we could have data exposure or data corruption, data loss. If we lose our keys, we can't get access to the data. We still have data loss. So we need to be careful with this. One thing you don't want to do is store your keys alongside your data. That's like having a file putting on the internet. Here's my username and password for these accounts. You just don't want to do that. So make sure your keys are in a secure location, in the secrets location, in something not near your data. Now, in the archive phase, we need to think physical security. If the archive is off-site and people can break into that off-site location, they violated your security. So where's the data going to be stored? Are multiple providers going to be involved? What are the environmental risks of it? Where your data is archived? Like loss of power, hurricanes, earthquake, I don't know, any kind of disaster that could be there. If you're going to archive your data in a different location, what are going to be the jurisdictional considerations, the location and the national laws? Is the data accessible during the contingency operations? Is it from the production environment for safety? Is the data need to be replicated to multiple locations? And does it matter where it's replicated? So We have to think about this in the archive phase. And, this is why our architects and cloud security architects and security architects, cloud architects, enterprise, all of us architects, it's why we're so far away from touching the technology and why we're always on the strategic level, because all of this stuff, everything we've identified so far moving through this is another question. And then we have to compare that question to either the business needs, legal, regulatory regulations, budgetary constraints, and so many more factors. So how are we going to archive the data? What's it going to be stored on? Is it going to be stored on physical media, like tape? Is it going to be stored on magnetic storage, like a traditional hard drive? Is it going to be offline? Is it going to be replicated somewhere? Do we use portable media? Okay. Let's say we found portable media that we put our data on. Now, how do we secure that portable media? Because if we do, then that portable media may need to be in a special high degree of safe that may also need to be protected by whatever. So we have to think about this. So where's the media going to be? What's the environmental locations? Meaning you have to make sure the environment can support the media and not destroy the media. How long will the data need to be retained? What data format will be accessible by what kind of hardware we might be using in the future? So we need to make sure we're not using wacky interfaces that we won't be able to find anymore on the servers in the future. Now, from a staff perspective, we have to consider whether we're going to staff this and who we're going to staff it. For example, do we have to use someone that was born in a certain country, or are we allowed to use foreign nationals? Sometimes regulations affect these kind of things. We have to ensure that any kind of provider we deal with performs the appropriate security checks, background checking, and ongoing monitoring if they're in place, because ultimately we're responsible for third parties, at least if our data is exposed. So typically speaking, we need to create a procedure and establish how the data will be recovered when needed. We need to determine how the data is going to be imported to the archive. We need to plan how we're going to do our backups. Are we doing a full backup, or we basically do a full backup every time? Are we doing these incremental or differential backups, which are more related to differences and changes with each backup since it's been created? So a lot of that we have to plan ahead of time. And where will the backups be done? Will they be done in the cloud? Okay, great. If I'm in AWS, I don't want to back up to AWS. I want to back up to Azure, Google, or somewhere else. I'm giving myself some extra redundancy, extra resiliency, and better disaster recovery ability. So maybe back it up and archive it on another cloud. Or at least think about that. And if you stay on the same cloud, potentially think about a different location where your other data is. But what always you want to have to do is you have to evaluate all the factors in the cloud, off the cloud. And as you start looking at things, you have to address any new concerns that would come in contracts. Okay, how do you destroy your data? Well, you destroy your data in the following matters. In the data center, you can take those hard drives and you can overwrite bad data, additional data on them for years. And for the most part, you could then reuse them if you wanted to. But we can't be erasing and overwriting our cloud providers' hard drives, 7 to 10 times with high degrees of this. Another option we'd have with our data centers is we just destroy the drives. We probably erase them first, drill them, burn them up, or something like that. We can destroy the drives. We can't do any of that on the cloud. So how do you destroy your data in the cloud? It's advisable to use crypto shredding or cryptographic erasure. And this is how you're going to do it. It involves using an incredibly high degree of encryption on your data and then destroying the decryption key. And that's called crypto shredding because it's got such a high level of encryption that nobody's going to be able to access it, including you, because it's destroyed. And then when you delete your accounts, if any remnants of that data are sitting on that provider's drives, which they will be, until it gets overwritten by something else at some point, many, many times in the future, at least at this point, nobody can access the data. So crypto shredding is how you get rid of your data in the cloud. So now I want to talk about different types of storage in the cloud, and we're going to have some fun here, and I'm going to show you which storage you typically use. And we're going to map it out because I want to make sure you truly understand it. So we have three kinds of storage that we're going to deal with. We're going to deal with block storage, object storage, and file storage. And for the purposes of the exam, they also define database storage, but database storage is typically stored on block storage. So we're going to do object storage. Oops, sorry about that. And we're going to have file storage. I'm going to show you how these work, and then we're going to talk about how to use them. So they're a little different in the way these storages work. What block storage is as follows. So typically speaking, let's say we've got a server, and this is our server. The server has a hard drive in it, or many, many hard drives. Now, when we take the data in a normal hard drive, and we take the data and it's stored on the hard drive, it's going to be file storage. Just like your notebook computer or any desktop, you store your data on file storage in your hard drive. But something that's very interesting, typically speaking, when you store your data on a hard drive, you store it in a block, in some form of storage blocks. And that's very interesting. We store it in blocks, but we write it to our local hard drive. So because of the way we store in blocks, it gives us the ability to do something else. So I want you to understand that in the server, we're limited to the amount of storage that's inside of the server. What we can do with block storage is what happens is we have these boxes, and these are going to be RAID arrays, and these RAID arrays are going to be filled with hard drives. And we could put so many hard drives in these devices. And what we can do is we can combine them in a way. We'll use some form of RAID where we're going to improve our speed. We're going to improve our redundancy. So this is going to be what the kind of storage the provider has. And what'll happen is we used to run separate networks called fiber channel, but in today's world, it's typically over Ethernet. Is we're going to have our switches, realistically speaking, our network switches. And the server would be plugged into a switch. The storage area networks will be plugged into the switch. And now what we can do is we can create this virtual hard drive. Now, the Cloud Security Alliance and the CCSK exam likes to call this volume storage. And I'll call it volume storage over here. But it's a virtual hard drive. And that becomes a virtual hard drive. And why does this work? So normally speaking, when we take data, we write it into blocks and we store it on the local hard drives. But with block storage, what we ultimately do, and it'll be mounted by the system as a virtual hard drive. With block storage, we write into blocks in a very similar manner that we would have not put it on the file on the hard drive here, but we're actually doing it over a network, and block storage enables virtual hard drives. So if you have a database in the cloud and it's running on a virtual machine, you're going to be using block storage for this. Now, this block storage is the fastest we get on the cloud, but it's not as fast as storage that's inside of the server. Now, the next kind of storage we have is going to be object storage. Object storage is different than block storage. Object storage is different because we take our data, and it's always going to start out as data. So we're going to have data, and when we store it as an object instead of a file. Which is one, don't know what happened there, which is one of the characteristics. Let me see if I can put this all in a single line. So we have space. So it's stored in an entirely different manner than what we're talking about. And that's okay. But when the data is stored with object storage, something very interesting happens. it automatically gets metadata. Now, this metadata can be significant in object storage. Now, because of this metadata or the data about the data, we talked about data classification, and this is way outside the scope of the Cloud Security Alliance's CCSK exam, but I want you to understand this metadata enables us to do many big data things. We can often query our data. Sometimes we can even run SQL type queries of our data stored in object storage. So, very valuable here. But the data is stored as an object. And something else that's very interesting about object storage is that it's worm storage. And what I mean by this is you write once and you can read it many times. And why is that? With traditional object storage, and the cloud providers have broken the rules, but object storage is immutable, meaning if I put a 4 terabyte object into object storage and I change that object by 1/10 of 1%, I need to now create a new 4 terabyte object. Now, this can be very, very beneficial or horrible. From a backup perspective, if you have immutable object storage and then your system gets infected with ransomware, it can't change what's on your object storage, for example, because it's immutable, the standard type of object storage. But we have to understand write once, read many times. So we can't mount this to a local computer for those reasons, because anytime we would change things, and things are always changing on our computer, a temp file, or this file, or that file, a swap file, it won't work. So object storage is going to be for backup, archival purposes. It's going to be used for big data, static website hosting, lots and lots and lots of good things. Now, here's the funny thing about object storage and the way the provider works. So you can pretty much look at this object storage as a big dumping ground. And what'll happen is the provider will put your object, so it'll have an object here, object A, and then we might have object B, and then we might have object C, and the key is it doesn't look like this is any kind of hierarchical storage at all, right? Because it isn't. What happens is all this stuff is just thrown into this thing. And what happens is there will be like a pointer to the data, much like in a database. So what'll happen is there'll be a pointer that says, to reach object A, go here. To reach object B, go here. To reach object C, go here. But object storage, widely used, big data, backup, archival purposes. Now, what brings us to file storage? So file storage is what the hard drive you have in your computer. And in file storage, there's two ways we're going to use it, but file storage is typically structured like this, and I'm sure all of you are very familiar with it. It's very hierarchical. You saw how in object storage we had zero hierarchy. Everything was just thrown in there and there was a pointer to the data. This might be different. For example, we may have the main drive, the C drive, or the root, and then under the root drive, we may have a user, and let's say the user is Cindy. My cat likes to use my computer all the time. She makes more spelling errors than me as she walks on it with her feet. And then Cindy has, Cindy's got, let's say she's got some folders, and inside of her folders, she's got cat photos because she likes cats. Well, not really. I like cats. She doesn't. I don't think my cat knows she's a cat, but maybe Cindy also has some documents. So maybe these are so Cindy has fish photos because she likes fish. Get rid of this. And if you notice, this is somewhat hierarchical in the way it's arranged. And then inside of cat photos, there'll be photos of cats. Inside of fish photos, there'll be photos of fish. So I want to go a little deeper into where you typically would use file storage in the cloud. In your hard drive, it typically makes sense. But let's say you've got the file storage server message block in Windows, or NFS in Linux. But let's say you've got a file server, and here's where you would use it. And then let's say you had 10 servers, for example, that needed the same information. And they all needed access to the same information. What you could ultimately do is you would use file storage to create a share, and all these other servers can get it. So when you need to be able to change data, move data, have this hierarchical structure where you've got 50 servers that need the same data, you use file storage. When you need backup and archival purposes, use block storage. When you need a virtual hard drive, you use storage in the cloud. So there are cloud storage types. These are also the same data storage types we've had for the last few decades. Now, on the cloud, we talked about long-term storage. Amazon Glacier, Azure Archive Storage, Google's Coldline, and Archive Tier. Remember, these are going to be used for backups, regulatory requirements, and cloud providers are going to have multiple tiers, and these are really used for low-cost long-term storage. We're also going to have what you call ephemeral storage. Ephemeral storage is stuff that's temporary. We're always dealing with temporary storage. On your hard drive, you have a swap file or page file where your computer can use virtual memory, use your hard drive as memory, as virtual memory if you run out of DRAM space and make sure your systems don't crash. Temporary storage. On the cloud, we have a virtual machine. And what's very interesting in cloud computing is the way this kind of works. So if we have our server itself, here's the cloud provider server. And we launch a virtual machine. The virtual machine typically has some kind of little mini hard drive that it came with. The problem is if we delete this and it's active while the virtual machine is running, it's ephemeral. And if I delete this virtual machine, guess what? I have no storage. Nothing's left over. So typically speaking, what you normally do is you don't put things that matter on ephemeral storage. So normally what you would do is you would take your virtual machine, you'll have your VM, you'll attach block storage to it, and then what happens if you delete the virtual machine, you'll still have the block storage available. And if you wanted to keep the storage volume, what have you. So that's often why organizations do this. But ephemeral storage is stuff that goes away.
Okay, well, we are back. So let's see if anyone has any questions. I will tell you that because everybody's been a little on the quiet side, which is really different for us, what we're going to do is we'll end up finishing tomorrow at approximately 3 p.m. So what we'll do is we'll do a career question and answer session where I'll be here. And if you want to know questions about how to be a security engineer versus a security architect versus a network engineer versus a cloud architect versus a cloud engineer, I'll be here to take those questions for you since I allocated the time anyway. And many people love when we do this because we find many people have spent years wasting their time by learning skills that are not at all related to the job they want. They're still good skills, but they're somebody else's skills. So we'll talk about what you need or anything to help you in your career for these 2 free hours. And tomorrow we'll do them from 3 p.m. to 5 p.m. approximately. And we will finish tomorrow at about, we'll start at 2 and we'll end the security program at 3. We should finish about 5:15 tonight in order to make all these things happy. So let's get to the questions and let's have some fun. Do some career stuff and some security stuff. Chris, if you'll bring in the first question, please. How are you securing your data warehouse? Is that the same like servers and infrastructure? So yes, and other things you might want to do. So we have to think about where the data warehouse is going to be. And if we manage it, and realistically speaking, if we're in a hybrid or multi-cloud environment, we're going to have to be managing it ourselves. We're going to have to do the following things. First, we're going to have to make sure that nobody can access the server itself except the people we intend to. So we'll use firewalls at any perimeter of our environment. We'll use access control lists in between subnets. Now, the server that's going to hold this, obviously, we're going to have to harden that server, meaning things like disable unnecessary services inside of that operating system, closing open ports, really locking that thing down. Of course, on the server itself, we'll have to put some endpoint protection, like a host-based firewall, a host-based IDS, IPS system, host-based malware, for example. and prevention, those types of things we need to keep on the system itself as well. Now, those are only two components. We're going to want to use a strong identity and access management strategy. We're going to want to use a good encryption strategy on our storage, good encryption strategy as things are moving in flight. But, we also want to secure the database and who can view it and how can view it. So not everybody needs to access the same views. So we may limit views to certain people. Some people can access all the data. Other people can access a percentage of the data. So we're not only enforcing the IAM on who can use what, but we're using the application to determine who can access what. Now, of course, there'll be integrations typically between that data warehouse and other tools, and we'll have to secure those APIs and integrations that go along all the way. So we want to make sure whoever's writing applications that are going to integrate into the data warehouse, that these are secure applications. They've had secure coding practices, input validation, sanitation, all those other kind of things that are going in there. So we're going to secure this the same way as we secure any other business application that's hosted in a server, in a cloud or a data center. And I only gave you a percentage of it, but obviously we're going to have to do the whole thing as we would to secure anything. The only good news is it's not like a web server, which has to be outside in a demilitarized zone. This can be completely private, away from anything that would be close to the internet, at least depending upon how we architect it. It's a great question, Senator Bissell. Any others? Well, if there are no other questions, give me a hashtag CCSK. And then we'll get back to the content. We'll get back to the content. Chris, roll with the content.
Now, we can talk about the storage inside the server, the direct access hard drive. You may think heard it called instant storage or other terms. This and the cloud is temporary ephemeral type storage for you. Now, in the data center, you could store on that raw storage directly on the server itself. Of course, where you store your information determines the complexities of your backup. So now we're going to talk about storage volumes, and that is going to be allocated storage space within the cloud represented as a drive attached to a virtual machine. So block storage, you're going to hear it called the storage volume, and I hope that makes sense to that. You'll see it in infrastructure as a service, for example, functions like a hard drive, but it's block storage, so it's just farther away. I talked about file storage and where we would use it, and I talked about block storage and what it is, and object storage is. So really, when you think object storage, make it clear to you. Backup, archival. Make it clear in your mind. Lots of metadata, which means ability to strongly label, strongly classify, and do many other things. Object storage, because of all the metadata. Strong indexing capability, which makes it very easy for us to put on information rights management, data loss prevention, and we've got some good degree of centralized data management. Now, in the cloud, we're going to have databases, and there's going to be multiple kinds of databases we can use. And either they'll be the same databases we've always used, and we'll put them on a virtual machine, or the cloud provider may even do it in a serverless provider for you, or we use a cloud provider's proprietary databases. But typically speaking, there are going to be many cases. Now, when it comes to databases, the primary two types, and there's I'll say three types, are relational databases, non-relational databases, and data warehouses. And relational databases are structured databases. Non-relational databases, we typically think of NoSQL, not only structured query language databases. And then we typically think about data warehouses, which are databases to store vast amounts of information to be able to make business inferences and run business intelligence tools to make better business decisions. So we have the opportunity to do a infrastructure as a service where we put it on a virtual machine, any database we want. Many are platform as a service, meaning it's already there, it's already to go, or platform as a service, where it's basically the database and it's serverless for you. And some are software as a service where it's basically 100% managed. Now, understand the second you use one of these cloud databases that's cloud provider proprietary, and you have more than one cloud, you have major integration challenges. You will need to create new software or middleware to translate between your databases, but use a standard database that works in all cloud, MySQL, Postgres, MariaDB, Microsoft SQL, Oracle. You can run them in all clouds and you have no integration challenges whatsoever. So much less to think about. So think about that. Now, when it comes to our databases, the bigger our data sets, the more data that could potentially be lost. So we want to minimize data sets. We want to use things like anonymization or pseudonymization to protect the data in case we were breached. So we really need to think about all of that. So I remember I talked about encryption. Encryption is going to make sure that the data can't be damaged. It's going to protect it at rest, in transit, and use, and we want to use that. Now, when it's in transit, communication between remote users or endpoints or anything like that, we should encrypt it. Inside the enterprise, we want to be able to encrypt it. Inside of the data center, we want the sway-on controls that are going to protect that data. Encryption reduces risk. Proper storage reduces risk. Proper access control reduces risk. The key and secrets management, whoa, that's going to be critical. So encryption keys must be stored with at least the same level of controls as the data. Imagine having data that's worth $1 billion, and all of a sudden we've done $50 of key control. And somebody breaks into the keys and they got our billions of dollars of data. So whatever amount of the key that we're using, type of encryption we're using, it has to be better than the data we're protecting, making it too hard or infeasible for people to get it. Now, the sensitivity of the data that we have will determine the required level of protection. Hope that makes sense fairly easily, that we have to deal with. And the effectiveness of any kind of cryptographic system is really going to be dependent upon keeping the encryption keys undisclosed. Because if somebody knows the decryption key, they have access to the data. Now, the only caveat to that is if we're using asymmetric encryption or public key encryption, the public keys will be public, can be shared, but the private keys must be kept private. So how do you distribute keys? Well, you create the keys locally. You can upload them to a secure location. You could potentially use a web service that securely enables you to save private keys in a secure environment. You could use a cloud key management service, but it's going to be essential to understand whatever services you're using and how secure they are and pick the right one. We also have to be able to revoke keys. So maybe we have a user. Maybe the key gives them access to sensitive material, and maybe we were like, okay, they no longer need to work here. That key needs to be revoked. Or person did something wrong, revoke that key. Or someone just left the company, revoke their key. So we need to make sure that people can't access things, and part of that is going to be key revocation. And we can, realistically speaking, just suspend the key or the ability of users to use it. And what will happen is the keys are going to be marked as revoked, and therefore the keys will no longer work. And this, from an implementation perspective, this can be centralized, or it can be put at multiple. That could be centralized. It can be. There's multiple ways this can be done, depending on the key usage, the distribution system, and its management. I want to briefly talk about key escrow. So these encryption keys are going to be pretty important. So we're going to have to find a way to store them. So key escrow gives us the ability to securely store our keys somewhere. And basically, we're going to put our keys in a trusted third party. If we choose to use this trusted third party as a secure environment for our keys. You might think of BitLocker keys for Windows workstations are kind of an example like this. And this is going to be common in cloud environments for incident response and legal holds, those types of things, key escrow. We also think about how long do we keep the keys to be valid? What's the key lifetime? So a key should have a defined lifeline and time and be replaced periodically. I don't want a 5-year key because if you compromise it at year 2, you get everything from the next 3 years. But if it takes you 10 years to break into a key and I change my keys every 3 months, we're going to be in a much more secure environment. So we want to do these kinds of things. So we could outsource key management as I described, but keys need to be stored properly, whatever we're using. Now, we can, some key management options is the customer can retain their keys. And that means the customer will have to put in this expensive infrastructure and hire the right kind of people that know how to do this. Now, theoretically, this would reduce the cost benefit of cloud services, but cloud services typically cost more anyway. And if it's required, here's an option that you have is the customer retains their keys. We can also outsource it to a cloud access security broker, and that's going to be a third party that's going to handle the IAM and the key management. In many cases, this will be the most cost-effective option. And cloud access security brokers typically have a lot of expertise in what they do. You can think of Zscaler, Netspoke, McAfee's enterprise cloud access security broker tool. Now, the market here is going to be dynamic. There's going to be a lot of changes in providers and things going on. So we have to keep up to date, obviously. I want to briefly talk about certificates. And certificates are typically used to identify individuals and users. They're going to be essential for cloud security and key management. And we will have, typically speaking, in a public key environment with certificates, a public key and a private key. And these keys can be self-generated or they can be issued by a certificate authority. And a certificate authority provides a certificate repository for certificates. They provide them, they store them, they distribute them, and you can come up with a certificate. You'll see these certificates on websites with that little lock HTTPS that you're typically using. Now, the key here is, which is great, is I can use a certificate, I can give a certificate, and then I can pull someone's certificate, and then they can't use it anymore, the encryption. So the way this works is something called the certificate revocation list, and it talks about the certificate status. And as soon as you find a problem, you revoke that certificate, and that will keep the person from using your cryptography. So we want to, from a security policy perspective, we want to design certificate management policies similar to encryption key management. Secure storage of private keys for the certificates. We have to understand the certificate revocation process for a breach and any kind of issue. And we need a lifecycle management option for the certificates. Create, distribute, and ownership responsibilities. Now, I'm hoping you're noticing, a lot of these phases of what we're talking about, a lot of these cycles, they're fairly similar, even regardless of the technology we're talking about. Now, I'd like to talk a little bit about hashing. Hashing, to me, is one of the coolest things I've ever seen. I'm not a mathematician, but the way these cryptographic hashes has always been fascinating to me. Let me give you some examples. So the way a hash actually works is, let's say we have the letter A here. And the letter A is put into a hash, and it's a 256-bit hash. And ultimately what happens is the letter A is going to go through this hash, and it's going to produce something that's 256 characters in length. So I'm not going to get to 256, but I'm just going to have a little fun and just put a couple of characters here. That didn't work. Bear with me. So if you notice, you get something that's going to look like this. Now, every time you put A in, it's going to come out and look at something like that. Every A will always produce this. Now, the reason I always thought this was mathematically cool is, unless you can break the cryptographic system, you can't go from this back to this. So it's only one way. And to me, that was the coolest thing. So what you're doing is you're taking your data, you're putting it through some form of a hashing thing, and you're going to get some kind of thing like this. Now, we can verify that the actual data is exactly what it's supposed to be because it's going to have the same hash. And that's going to be something cool. If this hash changed, somebody broke the data. So let's talk about why we need to make sure that the data is good. So let's say in your bank account, you've got $1 million, and I really hope you do. So let's say this is your bank account. And I hope you have more than that. But let's say this is your bank account. So you decide that you're going to pull out via online banking, $1,000, which, fine, you'll still have $999,000 out there. But what if when you went to take $1,000 out, decided to change that $1,000 and they changed the transaction log that you took $1 million out and now there's nothing left in your account and someone else siphoned it off? This would be a disaster. Or the other reason data integrity matters, we've got a physician and the physician prescribes a medication at 4 milligrams and somebody changes the 4 milligrams to 4 grams. And all of a sudden that's given to the patient and the patient has a major. So we're going to be using hashing to maintain data integrity. We're going to check and make sure a file hasn't changed. We're going to store the information and we're going to make sure our data is good with hashing. And that's going to be very critical for us. Now, typically speaking, the output of a hash is smaller than the input. Hashing is not encryption, although it's part of cryptography and used in the cryptographic system, but hashing should not be confused with encryption. Hashes are one way, but they can't be decrypted, which to me is pretty cool. Encrypting your data is turning it into mush so nobody can understand what it is without the decryption key. Hashing is a mathematical function to ensure the data's integrity. How else can we protect our data? We can use masking, obfuscation, anonymization, and tokenization, because using actual data can really provide some significant security risks. But if we obfuscate the data or mask it or anonymize it or tokenize it, it makes the data less meaningful should anyone actually get access to the data. So let's talk about randomization. Randomization replaces data with random information. It'll maintain attributes like the string length and character for realistic testing. So we take the data and we randomize it in a certain way, and all of a sudden it's no longer valuable to other people. That's hard to get to the actual source. We can anonymize the data. So what if we've got a database and it has the person's name, their birthday, their address, their phone number, and all this other business-related stuff? Well, maybe we want the business-related stuff, but we don't want anybody's name and phone number or birth date to come out of there. So maybe we kind of anonymize that information and we keep the rest of the data the same. So that's anonymization. Obviously, hashing is a great way that we can make sure the data is good. We can also shuffle the data, meaning we can use different data entries from the same data sets to represent the data. And this is going to create realistic test data, but it's going to use, because it's based upon actual production data, even if it's been moved around a little bit. We can also mask data, and you'll see this all the time. You ever log into a website and you see the last 4 digits of your credit card number and nothing else? That's data masking. They're not showing the full 16-digit card number, only the last 4, because the last 4 by itself aren't enough. We can also basically use nulls, where we delete some raw data from the display and show nothing. And this reduces the data set functionality, but it also increases security. We can also do something called tokenization. And with tokenization, what we're really doing is we're replacing sensitive data with a token value. And tokens are not going to be direct hashes to avoid any kind of hash-based attack. And this can be done statically, creating, like, say, an obscured copy of what we're dealing with, or dynamically obscuring the data as it's actually accessed. So we can do it in either way. Now, we're going to do these kinds of things. We can do it in a static manner, where we have a representational data set that's going to be created and used as a copy from the original. We can do some kind of dynamic configuration where data is going to be obscured during access to the data. Whatever we do, we have to keep these security considerations in mind. Sensitive information can be derived from mundane elements if they're not, even if they're obfuscated. Because certain things, you combine some elements of data here, another piece of data here, another piece of data here, another piece of data there, and all of a sudden you can start putting some pieces of the puzzle together. Anonymization involves removing non-specific identifiers, but it can be fairly complex. Do the user input in open fields. Marking data as sensitive creates metadata, which could potentially be useful for attackers. It's useful for us, but high value data, that could tell an attacker to try to break at it too. So we have to think about the key architectural trade-offs in every decision we make in cloud architecture, security architecture, what have you. Now, tokenizations, really, we could use two different databases, for example, with one with the actual data and another one with the tokens. And basically, the token server will authenticate the user program and retrieve the token and map it back to the actual data that presents it. This is going to add a lot of security and reduce dependency on encryption, but it will require some very strong authentication protocols for the token server. I briefly introduced the concept of data loss prevention. I'm going to talk about it a little more right now. Data loss prevention prevents data from leaving the organization's control, especially during the sharing phase. And this is going to be flexible for users on premises, flexible for mobile devices, flexible in cloud environments, because this is the reality of our world. We're trying to add an additional layer of defense to mitigate any accidental or intentional data outside the system. And we can enforce various policies here as we're dealing with. So the key here is data loss prevention tools give us some very good monitoring. They may be, for example, looking for data leaving the system, egress monitoring. They're going to be monitoring the logs going through things. And if we've got critical data for our business and we're in a highly regulated industry, understanding data loss prevention is going to be a big thing. And having these systems in place may help us get to better regulatory compliance. So our data loss prevention systems are going to identify data by using logging, pattern matching, similar techniques. They may monitor activity involving data or files, specifically or high-risk files. They're going to enforce organizational policies on the identified data. They can be automated, manual, or a combination of both. Some data loss prevention systems will search the storage volumes and production environments for data matching templates. And it can look for things like social security numbers or ICD-10 diagnosis codes or information that matters. It often uses categorization, classification, marking levels, and metadata. And by doing so, you can get a lot of information. Now, where we monitor for data loss prevention, there's really two places. One is called egress monitoring on the way to the internet. And egress monitoring, I drew it a little bit earlier, but a little bit earlier is basically where we have our system over here, our internal systems on the way to the internet where we're outside the network, whatever connections we have, we're doing egress monitoring. That's another one. But we can also put data loss prevention systems on the devices themselves. And we typically get some good learning with these data loss prevention systems where they will alert management or security personnel of any kind of violations that are going on. Anybody's trying to send sensitive information, alert management. They can warn users that they're trying to send sensitive information, and they can even block or prevent unauthorized access by, you can't send that attachment, for example. Now, cloud providers, for the most part, are going to restrict access to their data centers, which is going to make it harder for you to do certain data loss prevention and usage. You may want to disable every USB port on every device you have, unplug them from above it. You don't have that kind of control on the cloud providers. So understand that these data loss prevention systems are going to need significant processing power, especially if they're dealing with looking and pattern matching. So you'd be dealing with some pretty powerful servers here. Let's talk about some other types of storage you may see in the cloud. You may see platform as a service storage, meaning you might be using an environment and if the storage comes with the environment you're using. You'll be having storage for logging services. Think Amazon CloudWatch, Google Cloud Logging, Oracle Events, Azure Monitor. We will have message queues that we would deal with. In a multi-cloud environment, it's typically Apache Kafka. If we had a single cloud, which really doesn't exist for more than 2% of enterprises at this point, and we went the cloud proprietary way, we'd have message queues like Amazon SQS, Google Cloud Pub Sub, Azure Pure Storage. I think Oracle calls it streaming. And so typically that. We do have our software as a service storage that we typically think of. If an organization, for example, was using Office 365 and they had Microsoft OneDrive.
Okay, we are back. Looks like maybe there's a few questions that popped into the chat box, which I'm always happy to see. So we can answer your questions. If you just joined us, as a reminder, we've got a companion ebook that goes along with this course. My team will drop it in the chat box. And there's also the previous Monday, Tuesday, Wednesday of this CCSK Certificate of Cloud Security Knowledge Training course. So if you're just joining now, make sure you go watch the first couple of the days because we want you to be maximally successful. All right, and if you just got here, if you're enjoying the content, maybe give it a like. If you're not a subscriber, maybe subscribe and hit the bell to be notified of new videos. We've got a lot of things coming to help with your cloud architect career, security architect career, AI architect career, or other architect careers. Chris, bring in the questions. We actually answered that last session, Chris. Let's go to the next one. Would I explain the executive bundle and the enterprise program? So yes, I will explain the executive bundle, and what I will do is I will also invite you to speak to a staff member. So the enterprise architect program is a program designed to create enterprise architects. So it's basically our cloud architect training program to learn all the technical competencies of the architect and some of the business competencies, and then additional enterprise architect training and business architecture and business modeling and those types of things. Now, what our executive program is, it's basically our cloud architect program and enterprise architect program that has a lot of things. It's got our interview program. And why do we have our interview training? Because the more desirable you are in an interview, the greater your earnings will be. We also have our tech leadership program, which is a business school like. It's the equivalent. It's like a mini MBA program, teaching you the main components of an MBA, as well as the things that are not covered in an MBA program. We also have a marketing training program on building your professional brand, plus the cloud architect program. Now, the executive program, since you asked it, because otherwise I wouldn't talk about it on this, is taught by two main instructors, and it has daytime, evening, and weekend classes. And you can attend any of them or all of them that you desire. In the evening, David Lithicum teaches cloud architecture or AI architecture, depending upon which program you desire. And then during the day, I teach cloud architecture and enterprise architecture and business and leadership and executive skills. So it's a combination of a hybrid program with David Lithicum, who's basically Deloitte's chief cloud architect. He was Deloitte's chief cloud strategist, and me as an architect who's been an architect forever. And it's a program just like all of our programs that you take and you stay in until you reach your goal, which is moving into those architecture roles. Hope that helps, but I don't want to spend too much time on our YouTube training to go over things, even if they're good for our company. But make an appointment, and somebody from our team will work with you, and we'd love to speak with you, and I'd love to help you get to your goals. Chris, let's bring in the next one. What level of cybersecurity knowledge does a network engineer need to have? So it all depends on what level of a network engineer you are. I know network engineers that barely know how to turn on their computer, but their ability to design a network and actually be able to help the architects design the network and work on the network is so good that no one cares if they don't know anything about Linux or can't write a Python script, because they're the people that can help you architect your 10,000 router networks with 1 million routes on it and all your traffic engineering accordingly. So if you're dealing with an elite network engineer, and by that I mean entry level, started as the CCIE, that's your welcome ticket to the party, and then that engineer spends 10 years working on it, that kind of engineer needs to know nothing other than just networking. Now, if you're a standard engineer, meaning you're not going to be an expert, maybe you have like CCNP level knowledge, well, now at that point there's going to have to be other things you do in your job. So obviously, you're going to have to understand certain security things like VLANs, private VLANs, 802.1x, when you could use QoS for security, how you could shape traffic or police traffic, when you could use NAT, the types of NATs, the types of firewall policies that would use, the IDS, IPS systems. That would be things where you'd still be in networking, but you'd have a good level of security knowledge if you are that person that's not, where the CCIE is entry level to them. And if you know those things and you know networking strongly, you will have a great networking career. Now, if we're talking with someone with a CCNA level of knowledge, and that's what they consider themselves to be a network engineer, now at this point, the person's going to be doing mostly implementation. They're not going to be performance tuning. They're not going to do anything for the most part. They're just going to be configuring things. Now, that person, because they don't have any expertise in anything, they're going to need to know some Python. They're going to need to know some Linux. They might need to know a little DevOps. Then they might need to know a little bit about security and a little bit about some IAM things. So it all depends on how deep you want to get into your career and how strong you're going to be. That really is the key. But even if I'm dealing with a CCIE network engineer, and we have 2 internet peering points, and we're thinking, and we've got BGP peering, we can't just accept anybody's routes. We need to think about which routes to filter. If we don't want to become a transit autonomous system, and we have to think about, not sending routes outside of the networks that we took in from additional internet service providers, knowing what kind of ways that we can use to authenticate the peer and generally accepted standards for security, we still do need to know that. But the level of security engineer training that we're talking about is different. It's a specialty security. So I kind of hope I give you the answer to that. How can blockchain be implemented to in cloud security? So, this is an interesting one because the whole point of blockchain is to get it off a set of centralized levers. And then the cloud providers want to say, we're going to do your blockchain, which is pretty much centralizing it to one place. So if we really think about it, the cloud is kind of the worst place for blockchain. So where we call cloud blockchain is, if you think about it, if you use some of the edge computing that the cloud provider would have in a whole bunch of data centers and a whole bunch of regions, I guess you could call that as decentralized blockchain, because it is. And we're seeing a lot of those things. But if we really talk about blockchain, we're talking about distributed computers. Now, we can use blockchain to enhance security. And for example, it does enable us to track certain things, for example, because anytime a transaction occurs, it's going to be appended to the blockchain, and it's going to be immutable. It's immutable in the way it's written, so it can't be removed after the fact. It does provide a lot of tamper proofing because of the hashing and the way the logs and everything are stored along the way. It does provide for ways for smart contracts to ensure data access. And but if you really think about it, I don't really see blockchain in the clouds. I know the cloud providers try to say we've got blockchain services for you, but the whole point of the blockchain was to be distributed. If we look at why they came out with Bitcoin, it was because the people didn't want all the financial logs in the world all centralized in a bank provider's ledger sheets. Now, if we look at Ripple, it's 3 banks ganging together and or 4 of them and creating a centralized lever. It's the exact opposite of what Bitcoin was, or what Ethereum was, or any of these other distributed blockchains. So the cloud's a great place to do the compute, if you will. And but cloud and blockchain, to me, they're kind of opposites, that they're going in different directions. But we can use them concurrently to enhance security via some of the methods I gave you. Really great question there. Any others? All right. Well, if you have other questions, please feel free to bring them in. We want to do anything we can to help. Like I said, we're going to go to about 5:15 today, maybe a few minutes plus or minus in either direction. Tomorrow, we're going to go from 3 to 4. I'm sorry, from 2 to 3. And then from 3 to 5, we're going to do anything related to career questions, which is what a lot of people come to us for. So, Chris, let's get back to the content.
Now we're going to be entering Domain 10 for the Certificate of Cloud Security Knowledge, CCSK exam preparation program. And this is going to be about application security, predominantly in this section. So I want you to think about the cloud and these multi-cloud, highly distributed architectures as a fairly evolving and complex landscape. And there's going to be a lot of moving parts to security. We talked about IAM, there's network security, there's lots of components of security, but we have to have security into our application development. And we should cover application security, which is going to be the application's design, its maintenance, and everything along with the application and its lifecycle. And with cloud, applications typically move quicker. And that means we need security processes to keep pace with the application development. Some key things to think about. We could be working with microservice applications, and these applications are going to be interconnected little services. And that means we've got potentially a lot of different attack surfaces available to us as opposed to a single server or a single monolith. In the cloud, we may have a lot of APIs, and we may be using APIs, but they become an exposed attack surface that we need to think about. We also need to think about DevOps. Now, DevOps, or this continuous integration, continuous deployment, merging the development and operations together, enables software people to create much more rapid features, which is great. But now we have more rapid features. If they're not tested properly, we now introduce new risks. And now we also may have these platform as a service or serverless environments that we have to deal with in a provider-controlled environment that we don't even have access to. So that means we could be using open source libraries, or we could potentially use cloud-specific third-party things, or our third-party we may have third-party packages, libraries that we use. For example, we have to check the security of that. So obviously, we have things that are pretty easy in the cloud, like identity and management. It's integrated into pretty much everything they have. The cloud, typically speaking, is going to be a programmable infrastructure. So infrastructure as code can launch a whole lot of things very quickly. And in many cases, this cloud is scalable. We can do certain things in a stateless architecture where things aren't completely heavily tracked. So it adds a lot of flexibility to what we can do. But it also adds a tremendous amount of complexity. And this complexity can also reduce our security. So the key here is to talk about integrating security throughout the security development process. And from an architect's perspective, like a security architect or a cloud security architect, I need to ensure that the processes done by the security development teams are being there as part of our security policies about creating secure software. Now, if I'm an engineer in DevSecOps, now we're actually doing the work over here. So understand that if we're going to have secure applications, security is job one from the beginning, the time we even think about the applications. So I'm going to pretty much describe the secure software development lifecycle to you, and I'll go through what it is and its various stages, because I actually think this is pretty important. So the first thing we want to do in a secure development lifecycle is secure design and a secure architecture. So the first element is we have to create a secure design or a secure architecture. If this is off, no matter what we do, it's going to be bad. So once we know what the secure architecture is, both the cloud architecture, the infrastructure architecture, the application architecture, or how the application will be designed, now we've got to build the application. So that's the coding phase. And here we want to do secure coding. And I'll talk a little bit more about each one of these in a minute. But we want to make sure that it's coded properly. And we'll talk about keeping the coding clean. And at that point, once it's coded, at this point, it's going to be built, tested. So in DevOps, this stuff is pretty continuous. So I'll call it continuous build and testing. Because we're in DevOps, the goal is to speed it up. So the software will be built that was coded, then it'll be tested. And at this point, we're going to keep delivering these softwares and software to the organization, and we'll be constantly delivering, and so it's continuous delivery. And that's the whole point of DevOps here. And these types of processes to speed it up, to constantly CONTIN. To constantly get new features releases, make the business more agile. That's the actual goal that we're talking here. And obviously, We put stuff out there, we got to protect it, right? So here's where we got to defend it and constantly monitor it and make sure that things are going to be going on and things are good. So secure, I'm going to go in a little more detail on each stage. The secure architecture is going to add security at the design to make sure the application is going to scale, make sure it's going to be cost effective, make sure it meets some business need as opposed to just being some tech application that the engineering team built without knowing what the business needs were. For example, having a disconnect, which is usually the problem we have in most technology environments. 70 to 80% of all projects fail. And there's typically because there's a disconnect between the really genius, smart people that build these systems and what the business needs. But when they're not talking to each other, engineers build what they think, and the company has different needs. So that's why most technology projects fail. Typically the people process technology piece is missing. So after the architecture is designed properly, now it needs to be coded. Now here we want to make sure that we're using automated tools, at least the engineers are, to check the code and find vulnerabilities in the code early. We want to fix security issues during the coding faster. We may have other people evaluate what the developers are doing, pass the code around code checks, but we want to make sure that the code is clean as it's been coded. Now, when we get into this continuous build, integration, and testing phase, here we're going to be constantly testing the functionality and the security with automated tools of the system. And when we get to the continuous delivery and deployment phase, what we're going to be doing is run safety checks before we deploy something, because we want to make sure the applications are secure, the infrastructure is robust, and we want to avoid weak security policies that could lead to any type of an attack. And once it's up and running, we reach this defend phase, which the Cloud Security Alliance calls the runtime defense and modeling phase. But here the real key is to protect our applications after deployment with whatever we're using. We're going to monitor for vulnerabilities, respond to incidents, and consistently improve our processes. So when it comes to threat modeling, we need to know the kind of threats that we're dealing with. And threat modeling is going to be a risk management process that we're going to use to identify, assess, and mitigate security threats. And a lot of this is going to be focusing on the application and its risks during the system design. So there's a lot of steps that go into threat modeling. One is that we have to understand the system's architecture. We have to know what our security objectives are. If we don't know what we're trying to do, it's obviously going to give us some problems. And then we need to analyze the potential threats that exist. And we have to address vulnerabilities that exist effectively. Now, there are a lot of threat modeling methods. There is the STRIDE method from Microsoft. It's pretty common. And realistically, that involves looking for a few things. And the questions you want to ask is spoofing. Can the user's identity be obscured? From a tampering perspective, can unauthorized modifications be made? From a repudiation perspective, can the user deny their action after the fact? From an information disclosure perspective, does the application reveal sensitive information? From a denial of service perspective, can the application be shut down? Or from an escalation perspective, a privilege perspective, can a user gain unauthorized permissions? Now, Microsoft had an old model called the DREAD model, and it was based on damage, which was related to the severity of the attack, reproducibility, which is how easily someone could reproduce the attack, exploitability, meaning how easy it was to exploit a vulnerability, affected users, which would be the number of users impacted, discoverability, which was the ease of discovering the threat, and of course a scoring system from 1 to 10 based upon severity. There's another model that you might hear for threat modeling called ATASM, which means architecture, threats, attack surfaces, and mitigations. And the steps here are to understand the architecture, to list threat agents, their goals, methods, and objectives, to assess potential attack surfaces, to review security controls, and mitigate remaining attack surfaces. And here you're typically thinking of defense in depth. Now, another one which is incredibly common from a threat modeling perspective and very, very common is the PASTA method. And this is going to be the process for attack simulation and threat analysis. This tool is widely used. And there's basically 7 steps. And the first step is to define the business objectives. Great for any architecture thing. Define the technical scope of the assets and components, what needs to be done, to identify the application's controls, to perform threat analysis based upon threat intelligence, to detect vulnerabilities, to analyze and model attacks, and to perform risk and impact analysis and develop countermeasures. So we have the STRIDE system, which identifies potential threats during the software lifecycle. We have the DREAD model, which is an older, largely abandoned model, which is a risk rating system. And then we have the ATASM, which focuses on architecture and attack surfaces. And then we have the PASTA model, which for the most part simulates and analyzes threats over a 7-stage framework. Let's talk about some common threats to applications. And one is called an injection. And here we have a malicious user that injects code or strings of code into a field. And that can manipulate the application in a certain way. SQL injection attacks or attacks on LDAP or OS injections. The consequences typically here are data exposure or unwanted behaviors. So, input validation might prevent someone from injecting certain strings. We could also have the concept of a broken authentication. And authentication issues can impact users, accounts, or privileges. And this is going to be an exploitation based upon certain types of authentication weaknesses. We can have a common application attack called a cross-site scripting attack. And this is where untrusted data is going to be sent to web browsers without validating that information. And this is going to allow execution of some malicious code or potentially even hijacking the session. We can potentially have something called insecure direct object access, where an attacker can reference an internal object like a file without access control. Now, this is going to happen if we lack controls to prevent data manipulation by the attacker. Another main risk to applications is just security misconfigurations. This happens all the time, often unintentional by authorized professionals as a result of basic human error. Another type of threat we may have with an application is related to sensitive data exposure, disclosure of information such as personally identifiable information, medical data, credit card data. And this typically happens if we lack proper controls, encryption, data masking, tokenization, that kind of thing. Missing access control, you can see an application that may actually fail to verify privileges, which means malicious users here can forge requests and really cause some damage here. We could have what you call a cross-site request forgery. And that's where basically someone manipulates the logged on user, the browser information that's there to send a forged HTTP request. Now, ultimately, the victim's browser will be sending a request, but it's going to appear legitimate but it won't be. Another common problem with applications is where the developers get their libraries. Often developers get their code off of an internet, off of somebody's GitHub repository, and a lot of times there's actually security problems in the code. And these things can be a problem as well. So we need to know where we're getting our code from. Now, a lot of this is to make sure that we test out. So good quality assurance and testing processes. And when it comes to testing applications, we need a combination of automated tests that can do a whole lot of stuff real easily and some manual validation testing as well. We need to ensure that the software is going to meet whatever standards or requirements are needed. This could involve reviews, testing, reporting, and other activities. And there's going to be a lot of roles in quality assurance, and we need a dedicated staff for functional testing, non-functional testing. The developers need to review the code and unit test the code. The end users need to perform user acceptance and functional testing. So there's a lot of different methods. We have what we call integration testing, and that's going to validate the components and their interactions. We're typically going to do regression testing. So in other words, we add a new feature or a new version of what we have, and we're going to check and make sure that old bugs we've had didn't get reintroduced. And there's typically some user acceptance testing where the user tests the application and their interactions with it. We will typically have load testing where we basically assess the performance under load. For example, we used to use ISPs to generate traffic, detect networking things. I had a friend that was working, for example, at a company, and they had to spin up 15,000 virtual machines to try to stress test an application. Pretty cool to see how they launched all 15,000, tested it very quickly, and pulled it back. This was in the early days of cloud computing. Now it's kind of normal, but that's load testing, under load. And you can consider stress testing too, where you really push it under extreme conditions. So both things probably need to be done. Under extreme conditions, what breaks? Now, with regards to application testing, we're going to have static application testing as well. And this is typically speaking where someone reviews the source code, and that means the person needs to understand code reading, and quality. And this is often used to make sure the code is a sanity check on the code. We can also do something called dynamic application testing, and this is tests running on the code or applications. Typically speaking, it's automated and manual processes, and it can really validate the code functionality with real-world performance. We also have something called interactive application security testing. And what's going on here is it's going to analyze the code for vulnerabilities during use. It's going to provide real-time reporting information, and it could and should be integrated into the CI/CD process in order to make sure we've got automated release testing. This will analyze internal functions while the application is running. We also have the concept of an automated security code review. You may hear it called SAST. And this is known as static application security testing, and is typically a white box testing method that's going to examine the source code for security flaws, logic errors, and information. White box meaning you have a lot of information prior to doing the testing. And it's going to detect hard-coded credentials, like if somebody put a password string in the application, for example. It's going to look at the keys, tokens, and secrets to prevent any kind of repository leaks. And this is often commonly integrated into CI/CD pipelines or developers' integrated developing environments. You may hear it called shift left testing. And it helps to address the issues from that OS top 10 list and the SANS top 25. But this kind of testing may also cause false positives, which is to make you think you have a problem that you don't actually have. We may also want to do what's called this software composition analysis. We're going to track the packages in the software and in the applications. And this is going to be widely used for open source components to identify vulnerabilities in the components and, of course, the components' dependencies. So now I'll dive into white box testing. White box testing is full knowledge testing. You know everything about the environment to test it, the systems, the code. Now, we may have also called black box testing, which is called zero knowledge testing. Here you give someone and say, test this, but they don't know anything about it. They're using it as they're going to have to try to figure it out as an outsider. Now, abuse case testing is great, and here we use features in unintended ways. We try to exploit it. We try to abuse the application and see what happens. And then obviously we need to do some testing post-deployment, which we'll talk about next.
Okay, we are back. We want to check in on everyone, make sure you don't have any questions that you need answered. It's an awfully quiet group. So, I mean, hopefully we're doing such a good job that there are no questions, but if there are some, please ask. We really, really want to do anything we can to assist you in whatever your career goals are. So we'll see if there's any questions. If not, I'll remind you that we have a completely free e-guide to go along with this. It's a cheat sheets, several hundred pages of cheat sheets, but they're cheat sheets to assist you in your cybersecurity career, or as well as passing the CCSK or the Certificate of Cloud Security Knowledge training exam for the CCSK V5 certification. That's what we're doing here. So I just wanted to check and see. Just because we want to make sure that when you're doing this cloud certification, if you have any security questions, we can answer them for you, because we want to make sure you're doing well. So my team dropped the link to this guide. And I'll give you about 30 seconds to ask any questions. If we don't see any coming in, we'll go back to the content. If you're enjoying the content, maybe give it a like, subscribe to our channel, and hit the bell to be notified of new videos. If you know a friend that you think can benefit with this, please invite them, send them to this free training. That's why we do it for free. And of course, tomorrow we're going to end early. We've done so well. I mean, a lot of people didn't ask questions, so we went through the material a little faster than we planned. So we should be done we'll start at 2, done by 3 p.m. tomorrow. And I'm going to do what people really come to me for, is answer career questions from 3 to 5, because I've got people every day coming from all over the world asking us to assist with their career. So we'll be there completely free 3 to 5 p.m. tomorrow after we finish this boot camp. So I don't see anybody asking any questions. So please give me a hashtag CCSK so that I know you're awake, alert, and oriented. And we'll get back to the content, and we will have a great time with it.
Okay, now that we've deployed the application, let's talk about testing the application. And that's going to involve vulnerability scanning, penetration tests, and bug bounties. I'll begin with vulnerability assessments, and we're talking about it in the context of our applications here. These are going to be key security tools. We're going to be doing vulnerability scans. We're going to potentially be doing some penetration testing. We want to find the weaknesses in the system. So we find what the technical weaknesses are, then we know how to harden them. So assessment reports from vulnerabilities should include vulnerabilities, which are basically going to be the flaws or the gaps in the security that could be exploited by an attacker. And we're basically going to be using some automated tools to assist us in identifying vulnerabilities, potentially with other tools as well. And the outcome is for us to really create the strategy to go fix these things. Now, we have automated scanning tools for vulnerabilities, and these are designed to detect weaknesses in the systems, the applications, the networks, in a way that could be exploited by a hacker. And these are very efficient because they're automated tools. Automated scanning. So it doesn't take a lot of manual intervention for these tools. Now, we can do scheduled scans, do it automatically every single day at this time or hour or what have you. And the key here is to get some good reporting out of it, to generate reports and differences between different ones so you gain insights into the security environment. Lots of different types of vulnerability scans. We have network vulnerability scans that scan the devices that are connected to the network, like your servers, for example, but other stuff as well. And network vulnerability scans, which are different than network discovery scans, which we talked about, which identifies the devices in the network. Network vulnerability scans will look for vulnerabilities or weaknesses in the network infrastructure. We will typically also have done some web application vulnerability scans that are going to look for particular weaknesses in web applications. We will typically run database vulnerability scans that will detect weaknesses in our database systems. And understand there's going to be a wide variety of tools, a wide range of specialized tools for different types of vulnerability scanning. So it's going to put us in an environment where the organization needs to use the right tools for this type of environment to meet their needs. So let's talk about some network discovery scans. This is going to identify systems with open network ports. Ports could be used to compromise. The ports that are open could be used to compromise the system, so we typically have to protect them. Now, there's an old school scanner we typically use called Nmap, and that gives us a lot of information about the devices on the network and their open ports. We can also do something called TCP SYN scanning in networking. So if you'll recall, there's a 3-way handshake. And if you don't know, maybe I'll draw it out for you. So maybe it helped. We're used to it. Maybe it helped. So here's the way two devices set up a connection in networking. So let's say we have a host, and then we have another host. So this host is going to be very cool cattuna.com or whatever. This is going to be fancy cat tuna. Cattuna.abcdefg. So we're not using oh well, I don't know how I did that. Oh, fancy. Wow. So we have fancy cattuna.abcdefg, not .com, because we don't want to take somebody else's name by accident. And here we have a host, but in this case it's Cindy's PC. And Cindy wants to go buy tuna. So here's the way TCP sets up a connection. So Cindy says, I would like to open up a connection with you. So Cindy sends this, open up a connection with me, and it's going to be a TCP SYN. And what'll happen is the host for fancycattuna.abcdefg will say, okay, Cindy, I see your SYN, and I'm going to acknowledge it, but I'm also going to open a connection with you. So what that's going to look like is you're going to see from the server, you're going to see an acknowledgement from the fancycattuna.com. Yes, Cindy, I acknowledge the open, and I'm going to try to open a message with you, a connection with you, so we can speak. And then Cindy says, sure, you could open that message with me. And what Cindy does is she sends an acknowledgement back. And now, realistically speaking, Cindy and the tuna website are now talking to each other. So if we have TCP SYN scanning, what we're doing is we're sending out that TCP SYN or synchronize, and we're testing various ports. And we want to see if we get a response from the server. And this is known as half-open test scanning. Now, a DDoS attack can be launched by sending millions or tens of thousands of open SYNs to a server to try to take down its ability to handle too many open connections. So this is called as half-open scanning. We could also try TCP connect scanning. And this is basically going to establish a full connection to the remote system on the port. And this we would use if the scanner couldn't create a half-open scanning environment. And many scanning types need raw packet sending capabilities, and some operating systems may actually restrict this. So we could do TCP connect scanning where we just establish real connections. We can also do what's called TCP ACK scanning. And we can send a packet with the acknowledgement flag and making it look like it's part of an ongoing connection. And this can help us identify various firewall configurations and things as well, because old school firewalls used to look for those. Now they typically track the state of the connection. Now, TCP is used for connection-oriented, reliable information. I need to send a file and guarantee that it's received on the other end. I'm using TCP. If I need to send real-time information where I don't care if it's lost, like a voice conversation or a video conversation, I typically use UDP. It's connectionless and it's fast. So I might be scanning UDP ports as well to see what responds on the servers. I may also do something called Christmas scanning or XMAS scanning. And basically this sends a packet with the FIN, the push, and the URGC flag set and the packet header. And it's designed to light up like a Christmas tree. And realistically, the name comes from the packet's ability and its false appearance because of all these flags that are set. Obviously, we can also do network vulnerability scans that are going to extend beyond just identifying ports that are open. We're going to be using data sets containing thousands of vulnerabilities to try and detect various components and weaknesses on the system. Weaknesses in the routers, weaknesses in the switches, weaknesses in their operating system, or the microcode that could be there. So it's a process to detect these vulnerabilities. We're going to have scanners that are going to run tests from their databases. And sometimes scanners will tell us that a problem that doesn't exist really exists, a false positive. Sometimes it'll miss real problems, and then you get a false negative. So the key here is scanning isn't always going to be perfect. Now, there's lots of scanning modes and their effects, and by default, network vulnerability scanners are going to perform unauthenticated scans. And they're going to test target systems without needing passwords or specific access. Now, these scans are designed to simulate an attacker's perspective if they didn't have a user's account on the system. Now, how do we improve our scanning accuracy? Well, conducting authenticated scans will be much more like the real world. And in authenticating scans, the scanner is going to gain read-only access to, the scanner will probably gain read-only access to the servers, and that's going to enable it to gather and utilize configuration data from the target system to better analyze what's going on. It's much easier if you're authenticated. Now, web applications have their own risks and therefore need to be scanned. A lot of it's because they're connected to the internet versus a private network, but it's part of it is the nature of the web application. So web applications need to be scanned. We need to know the risks that are associated with them. And we need security appliances like firewalls that will allow our devices to be hardened and protected to protect them. So with web vulnerability scanning, we typically check the servers and we scan them and we try to see if things happen. We might try to inject SQL injection things like to see if that would occur. And we're trying to see if the web application has weaknesses that need to be fixed. Now, there are lots of vulnerability scanners that can detect vulnerabilities in web applications. And web vulnerability scanners are going to be a critical part of our testing process, as they can uncover things quickly and easily that we may not know about. Now, during the scan, these tools may employ an automated technique. They may manipulate various input parameters, and they're trying to identify weaknesses in the system. And after scanning, we'll typically get a tool, which will make recommendations on the problems and remediation. But again, we're going to have to check that. We also want to scan the databases because the databases hold a lot of critical information. And there's often a database behind a web application. And while firewalls protect the databases from direct external applications, if the web application is a gateway to the attack, we would have a problem. So maybe I'll explain to you what I mean by that. A typical web application is often 3 tiers. We typically have the web tier of the application, which is what the user sees. And this presents the website. We typically have some application servers behind the web servers that run the business logic. And behind the application servers, there's typically a database of some kind. And realistically speaking, the firewall is going to keep you from accessing the database server. But what happens if you get to the web server, and then from the web server, you can jump to the app server, and then when your source IP address is the app server, and now you're hitting the database. So firewall does, and databases contain a lot of information. So we have to scan our databases. We have to check for vulnerabilities. We need to be sure that our databases are rock solid. Now, another great way to really figure this out is through something called penetration testing. And penetration testing is called ethical hacking. We pay somebody to break into our systems and then tell us how they did, because they identified the weaknesses of the system to break in. And because they are ethical, we're paying them. They're going to do things in a secure manner and report back to us. So they're going to identify lots of vulnerabilities they're going to find, and these could be vulnerabilities in our people. Maybe they use some social engineering to talk to people to talk their way into something or get someone to give them the password. Maybe they used a phishing scam and somebody clicked on a link and provided information. But the point is, we have to figure out exactly what we're dealing with. And if we think we have effective defenses and somebody can break in, then we clearly don't. So again, that's going to help us verify our defenses. And now from a compliance perspective, it's a lot easier to say, well, we've done this, we followed all these practices, we've met these international standards, and we paid someone to break in, and we even found and remediated those weaknesses, and now they can't break in again. Ultimately, someone will always be able to break in if you put enough time, effort, and money into it. But the goal of security is to make it infeasible. So it costs more to break in than what you're going to get. We may try to break in with a network service test where we focus on network-specific exploits, putting in bad routes, switches, manipulating the firewalls, a web application test, client-side test. We're going to try and cross-site scripting attack, SQL injection attack. If there's an attack, the penetration testing is going to try it. They're going to try to break into the wireless systems and see weaknesses in the wireless. They're going to go to the social engineering environment and try to talk to people and see if they can find a way in that way. So penetration testing is a great way. We hire a hacker to break into our systems because they think like a hacker, because they are a hacker, and they can tell us deficiencies we have. So let's talk about the phases of penetration testing over here. The first phase is planning and reconnaissance. If you're going to break into something, you need intel, right? So you plan, you gather facts and information, and that's the reconnaissance phase. Now, after you've collected the information, the hackers collected their information, the next thing is a scanning phase. Here, typically speaking, we're scanning, we're looking for vulnerabilities that we can exploit, we're looking for weaknesses in the system. Now, we've done our recon, we got our information, we found the vulnerabilities. Now the next phase is to break in. And we're going to try web application attacks like cross-site scripting. We're going to try network attacks. We're going to try people attacks. We're going to do anything we can to break in from an ethical hacking perspective. I mean, the ethical hackers, not the architects. But at this point, once somebody gets in, we want to see if they can maintain access and be undetected. You may have heard the term advanced persistent threat, where someone breaks in and they're constantly on your system monitoring what you're doing, and you don't even know they're there. And in many cases, it takes 6 to 12 months to detect that an attacker is there. It's not uncommon. So we want to see if we can detect them. And if we can't detect them, we want to harden that ability to be able to find them faster too. And then afterwards, the last phase is really, the phases are going to be more analysis. What were the vulnerabilities that existed? What kind of sensitive data was accessed? How much time was the hacker in undetected? Because that puts us in a place to create a report, follow up on that report, and go do something about it, where we prioritize the weaknesses one by one and figure out how we fix them. So think about penetration testing and being the verification that what you did actually worked. Let's talk about a couple different kinds of penetration tests. We have what you call white box testing. And it was very similar to the software testing we were talking before. White box penetration test is where basically you give someone access to every piece of information about your system. And that means the person may not need to do the initial reconnaissance. It's going to speed up the testing process. It's going to mean it's going to cost less testing wise, typically, because it's going to take less hours. And it will really find the weakness, because this is what you call a known environment test. If you know anything, everything, it would be a lot easier to break it. And this could be an internal employee's perspective, if you will, where they know everything. If you had an internal employee that knew everything, they're trying to break in. Now, by comparison, we have something called the gray box penetration test. And this is where you give the ethical hacking team a little information about what you have. It combines some elements of some known knowledge and some knowledge of unknown knowledge. This is what you call a partially known environment test. And there's a lot of benefit here, because we got a lot of good security, we got a lot of reliability, we give people good amount of information like a hacker might have, like partial knowledge that they would get from recon, and then they attack. And of course, we can do black box testing, which is where we provide no information, which really simulates the real hacker environment. But we have to be sure that what we're doing is working. Now, we always want to think about our architecture. Remember, cloud computing emphasizes treating all components as software, and it's basically virtual stuff. So when you think about it, if we're getting distributed, it's going to be more places that we have to protect. Getting scalable is one of the benefits that we actually get. So we want to think about everything. We want to think about the applications components and their credentials. Do we need any permissions and credentials in between systems? And we want to manage that and be careful how we expose any information. We want to make sure that if we're dealing with microservices that require permissions or credentials, that they're properly managed, because mismanagement of these credentials will lead to exposure. Infrastructure, it should be deployed as infrastructure as code when possible, because it will automate the process. It will allow for efficient security integration and making sure things are consistent and we don't have variations which could cause weaknesses. Immutable architectures are great if we create it that the systems are not modified after creation. Instead, if there's a change, we create a new version and we shut the old systems down. Lots more reliability and security because you know what you're actually dealing with. We talked about it before, but secrets management is going to be critical. We're going to have digital credentials like passwords, keys, tokens. We need to keep that, because if our passwords get out or our secrets get out, well, basically people can access our systems. So we have to think about our key policies and our secrets management. We want a systematic creation, distribution, rotation, and revocation of credentials. We want to be able to detect and prevent any kind of secrets leaks. When we're dealing with cloud providers, they've got their IAM solutions and their identities and their secure storage solutions, but we always have third-party solutions. And in many cases, these third-party solutions could be incredibly robust. We talked earlier about DevOps combining software development, the development side, and the operations in the same process to speed up the software development lifecycle, and that focuses on collaboration, automation, and agility and scalability when the applications are being built. We also have what's called DevSecOps, and DevSecOps is not security. DevSecOps is related to security through the applications lifecycle, the software development lifecycle. And this is adding security and much more security testing and much more security integration into the DevOps process, which is an absolute wonderful thing. But it's only a component of security. There's really 6 pillars of DevSecOps, and they're introduced by the Cloud Security Alliance to guide security professionals. One is automated deployment pipelines, which automate security checks, scans, and tests to ensure efficiency and security. The other is the continuous integration and continuous delivery, which is going to ensure reliable application deployments with minimal and manual intervention. And that's common in cloud environments, that minimized intervention. Another thing that we want to talk about is a shift left with regards to security. And that's going to encourage integrating security earlier in the software development lifecycle. Focus on creating secure software by design, secure by default. So this is proactive security. And that means continuous monitoring. We're going to be dealing with static application testing, for example, and other things, continuous deployment, constantly producing new things. Much faster software releases, but of course, we have to be very careful in how we're doing it. So we have to make sure that whatever we do is going to be secure and get us to where we need to. Now, we have to be able to deploy secure images as well. So we need to make sure that we've got a secure image container configuration, and we're going to package our applications and all of the dependencies in a secure manner. So what does this mean? If we've got a virtual machine, we want to have a secure image. If we're dealing with a container, we want to make sure that we're secure in the way we pack it up. So the application source code should be checked. We need a version control repository to make sure that whatever images we're using for our virtual machines or our containers are up to date. And we're using a version control system like Git or something like it that's going to enable us to check our configuration changes, collaborate better, and be accountable to our systems. And we typically need some form of a continuous integration server that's going to automate the image building and the image security checks whenever changes are going to be committed using some type of continuous integration tool. We want security testing and enforcement. We want to conduct security testing, static testing, dynamic testing, vulnerability testing, software competencies analysis. The key here is to identify issues earlier. We want master images, create secure, hardened images, virtual machines, container images, and we want manual or automated acceptance testing. And we have to be able to deploy to production and make sure that our systems are good and secure. So let's talk about protecting web applications and API gateways. Obviously, we're going to use a lot of network security. In many cases, we're going to be using network next generation firewalls, but we can also use WAFs, which is a web application firewall, which we may put on certain things. WAPs typically focus on protecting websites with web application specific checking at layer 7. In many cases, they're more specific than your traditional next generation firewall. Having said that, the WAF protects the application, but not the systems on the environment. So if you look at it this way, if we have an environment here, and here is our entire data center or our entire VPC, when we go out here if here's on the internet, oops, bear with me, and then we've got a firewall, what we're typically dealing with over here is We've got very good, strong boundaries. And over here, you would typically have your load balancer, and your load balancer with a public IP address. And then behind it, you'd have your little web servers, which often might even have private IP addresses because they're behind the load balancer. So let's say you have something that looks like this. This is pretty traditional environment. The web stuff is outside of your data center, your VPC, if you will, or it's in a different VPC, whatever we have to do to microsegment on it. This is very common. And this firewall that we're using, or this pair of firewalls, or whatever we're using, is protecting our internal organization. And typically what will happen, let's say these are web servers, let's say they're accessed via HTTPS, this area called the demilitarized zone will allow traffic from the internet on, say, TCP port 443 only to these web servers. And that's what that next generation firewall does. Now we have the ability to put a slightly optimized firewall, maybe on the load balancer, maybe on the web servers, maybe on an API gateway, depending upon what we have, that's going to be a little better at looking at just web applications than this firewall, which is designed to do everything. So what we could do is we could put a firewall here and a WAF here, web application firewall. Understand there's very different grades of WAF. There are WAFs that we can get from industrial third-party providers that, literally speaking, are adaptive in nature and can attach attacks in real time. The cloud providers also make a WAF, but it has much less behavioral analysis, anomaly, and they don't have the ability to mitigate the unknown threats the same way that maybe a WAF from a Palo Alto, a Cisco, a Fortinet, or a Checkpoint can. Now, this is obviously dynamic and constantly changing over time. So whenever it comes to choosing the right firewalls that you're going to be using, you're going to deal with multiple vendors, talk to their solutions architects, get information, and then ultimately have somebody in your team test them. But understand that we can use web application firewalls to protect web applications, typically speaking. But we also probably need to use real traditional firewalls as well. So we may have lots of deployments that we could be dealing with. We could put an agent, for example. It could be a cloud provider service that's providing the WAF. It could be a third-party marketplace service that you would be getting from, say, like an AWS marketplace or an Azure marketplace. And there are even companies that are doing WAF and distributed denial of service, attack prevention as a service.
Okay, well, we are back. So we are here to answer any last minute questions for the day. It's been fun going through this from my end. I hope you're all learning and having fun at the same time. So, Chris, bring in any questions if they exist. Do ethical hackers do testing on apps? So, yes, in many cases, we do pay penetration testers to test our environment. So, it depends on what you're going to check. You're generally using your ethical hackers or your penetration testers to test your entire system, to try and flirt with the receptionist, man or woman, for example, and see if they can get in or if that helps them, for example. That's called, say, social engineering. Or could they get into the system, or where are the weaknesses in the system, for example? So we could use ethical hackers on the apps. We can also use code scanners and scanning tools internally on the apps themselves. So what's probably a better thing to do is to actually create the design, test everything along the way, and then have somebody try to break into the system to truly find the weakness. But at first, use all the internal tools, scan everything, think about everything, fix everything that you can think of. And then after the fact, it's like, okay, not before you get hacked, but after you've created your architecture, then use that to find the weaknesses in the system that you didn't already identify. But ethical hackers do testing on apps, but they're also testing, can they use the app to break into the system? Can they crash into the system? How could they get into the system? So a lot more into ethical hacking. But yes, they could also be testing on the app. Good questions there, Parviz, as always. I know you're super smart. Will network engineers die out? So while I have concerns for a lot of engineers, network engineers are going to be safe for a long period of time. And here's the reason why. Well, AI does a great job at coding, and companies like Google are writing 25% of their code right now with AI, and that's only in its infancy. And as GPU performance gets better, and models are trained better, expect it to be a lot more than 25% of the code that's written. But networking is really complicated. And, if I interview 1,000 people that are, say, CCNA or CCNP certified, chances are, guess what? We still don't find one single person that even understands network engineering. The pool is so low. So there's a need for it. Now, understand that not a single cloud works without network engineers creating the network. And it's not like software, which can be done easily. Network engineering is a lot of deep analysis. So it goes very, very deep. So we need network engineers for the internet service providers. We need network engineers to build the clouds and design the clouds of the cloud providers, like I designed cloud providers and clouds for the last 25 years. But we will also need the network engineers for all the private clouds and all the cloud repatriation, because everybody's building a private cloud now. And we're going to need a new set of network engineers there. And guess what? No one knows networking. So you're always going to be safe in networking if you're great. But here's the difference between the people that are safe in networking and the people that are not. The sales engineer that works for Cisco, safe, because they're selling a product, they're attached to revenue. The principal solutions architects, like I was in networking, are going to always be safe because we're designing things, we're meeting people, we're managing stakeholders, we're selling things, always safe. Now, here's the network engineers that are safe. The ones that really, really, really know networking. The ones where I can ask at a moment notice, tell me all the SLAs that exist in an OSPF area and what they do. The ones, if I say, okay, in OSPF, what does it do that's more link state, and what does it do that's more distance vector? And if they explain the protocol. Do they understand the impact of the LSAs? Do they understand the impact of keeping the LSA database small? Because things get happen. So when I'm dealing with that kind of person, and a person that understands BGP, that understands traffic engineering in BGP, that could set up peering to 8 different internet service providers, that knows about BGP security, and knows how not to become a transit AS, knows how to not let bad routes injected. When I'm started talking about that person, then we're really dealing with someone that's irreplaceable. Now, if we're just talking about someone that just knows how to do basic configuration, that person is never going to be safe, because AI can do that kind of stuff. So it all depends on the level of network engineer. So, Mr. AB, here's what I say in network engineering. When I first took the CCNA, I thought I knew something about networking. I didn't. Then I took the CCNP, and I thought I knew something about networking. I realized that there was more to networking than I knew. And then I became a CCIE and my number is 7417. And I went, oh my God, I don't know anything about networking after passing the CCIE. Because as soon as I passed the CCIE, I got put on a project that was about 800 times harder than any CCIE exam. And I went, it's time to learn. So, and I don't care if you've got a certification. I don't care if you don't. For example, I had a friend, Ted, and this guy was so great at networking. I don't think he had a single certification in his life, but I'd put him up against any CCIE in networking. He was that good. His knowledge was that good. So great networking people don't have anything to worry about. Will always be being needed. Nothing works without the network. Nothing. Good question. If a load balancer has a public IP address, does it NAT and host? So exactly what's going on, Parvi, is very well thought. So let's say you've got a load balancer, and the edge of it has that public IP address, and now you have 100 clients behind that load balancer. The load balancer is effectively NATing or translating those private addresses into a single address when it goes out and is seen for the rest of the world. So yes, it's actually doing some form of NAT. Very good questions. But not all load balancers necessarily have to be doing that based upon the way you would set them up. But generally speaking, yes, they're doing that. These are good questions. These are good questions that make me know that you're thinking, and you know that you're actually learning the concept. So great job, everybody. So if there are no other questions, what we'll do is we'll finish. And then after we finish today, we'll come back tomorrow. We've got about an hour from 2 to 3 tomorrow. And then after that, we'll do a 2-hour separate session on career questions, goals about being a network engineer, network architect, security architect, enterprise architect, cloud architect. I don't care. Solutions architect, any job you want. I just want to help you get to your goal. I've been in this technology thing 25 years ago from when I left practicing internal medicine. And I spent about 2 decades helping all kinds of people all over the world get their first tech job, get promoted in tech. And I want you to love the tech career you have as much as I had. Because to me, it was the greatest thing that ever happened to me. People actually paid me for a hobby of mine. I got to meet people, travel the world, design systems for people, and they actually paid me to do it. And to me, I just thought it was so much fun. I was just thrilled to have that opportunity. So take care, everybody. If you enjoyed the video, please give it a like. If you're not a subscriber, subscribe. Hit the bell to be notified of new videos to assist you in your technology career. And I'll see you